Satellite communications are approaching a data rate wall with our existing RF technology, and our best solution may be space lasers. Fundamentally, data rate is a function of baud rate in symbols per second and spectral efficiency, bits per symbol, which gives our data rate in bits per second. And there are physical limitations for both of these terms. To give you a good sense of this, we're going to start with my link budget simulator from the last video. And in case you missed that video, we'll just do a quick refresher on satellite communications so that we're all on the same page. So what I have here is a scenario for a Starlink downlink, and this is all based on FCC filings, so this is all as accurate as we can be. So on downlink, you will have the transmitter in space that will have some transmit power, and then it'll have a gain pattern for where it is aiming, and then also determines how much the signal is spreading out through space. The user terminal will also have a gain pattern, and this will determine how much power it receives in which direction, and then the identical gain pattern is used for when the user terminal is transmitting to the satellite, and then the satellite would be receiving, and that's called uplink. So to calculate the power received, you could do this very predictably in RF using the Friis equation. So you will have the power of your transmitter, the gain of both the transmitter and then the receiver antennas, and then here you have the free space path loss term. Something to notice is that you have 1 over r squared, that's the slant range. So to show a quick demo of this, here we have our range set to 350 kilometers. It's looking straight down, so that's the slant range. And then you can see the size of the swath here. Now, when we double that slant range to 700, you can see the size of this circle expanded by 2 in both directions. So the area is 2 squared, or 4 times bigger than it was. And so the power received at any given antenna in this swath will be 4 times less. You also have wavelength squared in the free space path loss equation, and that could be a little unintuitive, but you can also see that since the wavelength squared is also in our gain equation, when we hold the size of the aperture fixed and we change the frequency of our transmitter, that will change the gain. So if you hold the gain fixed, as we do in the math, then when you change the frequency, that will change your power received because the aperture size is then changing as you change the frequency. Okay, and then finally, the rest of the power received equation, we just have the losses from the atmosphere and then some other miscellaneous losses, and we have some basic assumptions for those. Next, we want to calculate the signal to noise ratio, and we can also do this very predictably because in antenna systems, in either microwave or radio frequency systems, the dominant noise term will be the thermal noise. So on the top of the equation, we'll have our power received, and then on the bottom, we'll have our thermal noise density, which is the Boltzmann constant times the system temperature. Here you see we have the symbol rate, and that's because we were calculating the signal to noise ratio per symbol. The symbol rate will be equivalent to our occupied bandwidth. So you'll have some center frequency for your carrier wave, and then if you modulate 5 billion symbols per second onto that carrier wave, for example, that will occupy 5 gigahertz of bandwidth. Once we have our signal to noise ratio calculated right here, we can start to calculate our bit rate. To do this, I'm using the Open DVB S2X satellite communication standard, and our assumption is that this will be somewhat similar to the Starlink proprietary standard. So in this standard, they use amplitude phase shift keying. So in these rings, these will be the amplitude of the signal, and then the angle around these circles will be the phase. We know from academic research that Starlink does it a little bit differently in the Constellation, but they're still modulating the amplitude and phase of their signal. Now, what these communication standards do is that they change the modulation type and also the forward error correction based on that signal to noise ratio. So as I just changed the transmit gain, for example, you can see we start off by only modulating the phase. This is quadrature phase shift keying. And then as we move up, we can add more and more symbols. As we add more and more symbol options, these symbols will represent more bits per symbol, or bits per hertz, as it's listed here. And so 64 gram, that's 2 to the power of 6, so that's 6 bits. If we move up to 256 gram, 2 to the power of 8, that's 8 bits. And you can go further and further. If you extend this, this isn't part of the official DVB S2X standards, but you can go all the way up to 4096 gram. That's 2 to the power of 12 is 4096. And so that's up to 12 bits per symbol, 12 bits per hertz. We'll cover forward error correction later in this video, but you can see this ratio. This is the ratio of data bits to total bits. And so in this case, we'll use 1 parity bit for every 6 total bits. That will allow us to correct errors. And this standard uses low density parity check as its forward error correction. And that is very close to the Shannon limit, which is the absolute mathematical limit of forward error correction. So we know that the Starlink proprietary standard cannot be much better in terms of signal to noise ratio to bit rate than this open standard. And so that's why it's a good assumption for practically every low Earth orbit RF system. Something I want to emphasize is that the spectral efficiency term here will have a trade-off with power efficiency, and this will become very important in optical communications. So I just want to show you how this relationship works all the way through the range of modulation options. We'll start out at 0.1 watts, and here this will equate to 1 bits per symbol. Now, let's bump up the power by a factor of 2 over and over again, and you'll see how the spectral efficiency changes. So here we'll go to 0.2 watts. We now get around 2 bits per hertz, so that's doubling. That's roughly a linear relationship there. Now we'll double again. And this time it didn't double, it barely went up. It went to 2 bits per hertz. Now we'll double again to 0.8 watts. Okay, now we're at 2.5. And as we continue doubling, you will notice diminishing returns in our spectral efficiency. And this can go all the way up. We'll go a bit faster now. We'll go all the way to 50. We'll go to 500. That will only get us to 8 bits per hertz. What I want to emphasize here is that there's diminishing returns to getting higher spectral efficiency. And the trade-off is how much bandwidth do you want to use versus how much gain and power do you want to use. Okay, that ends our satellite communications review. And now we'll get into the limitations on bandwidth. And the first of these will be your antenna hardware. So to demonstrate this, I have a preset of the Starlink direct-to-cell antenna. This antenna is designed to operate in a range centered at 2 gigahertz, and it can only operate between 1.5 and 2.5 gigahertz. And this is just a physical limitation of antennas. They can only efficiently receive and transmit photons within a specific range. These antennas, they typically only use a very narrow range of bandwidth for legal reasons, but if you tried to modulate, for example, 5 billion symbols onto this carrier wave, so 5 gigahertz, that's physically impossible because at a center frequency of 2, that would require negative frequencies. And then practically speaking, you could only really use 1 gigahertz at best because of the antenna design. So to use more bandwidth, you need to either use more antennas at different center frequencies and or use higher frequency antennas. So for example, at KU band, this is centered at around 12 gigahertz. And so they can use around 3 to 4 gigahertz between uplink and downlink. As we move further, say V-band can use up to 10 gigahertz. And then out at W-band, this is their special backhaul antennas. These can use around 20 gigahertz. The next limitation on bandwidth is the atmosphere. So that's the atmospheric path loss that was in that equation we covered earlier. So at somewhat low frequencies like KU band used for the Starlink user terminals, there's not very strong atmospheric effects in most cases. However, if we move up in frequency, you can see that we can run into some problems. For example, here we run into an oxygen absorption band. That's going to be basically completely block our signal by the atmosphere. As we move up, that'll mitigate. However, when it starts to rain, that can have a significant effect and it can potentially completely knock out your signal. Now, I want to emphasize that this isn't a hard limit on the atmospheric loss. So you can see I'll jack it up all the way to 50 decibels of here. That will knock out your normal signal. However, you have some options to mitigate this. First of all, you could just simply increase your power to restore your signal. Alternatively, you can decrease your bandwidth, and that will focus more energy into a smaller bandwidth range, and that will also mean less noise bandwidth. So that will allow you to restore your signal even if you have a severe atmospheric loss. However, at 50 decibels, that means 99.999% of the energy is being blocked. So very few links will be designed to have this much margin. And so we will treat this as our practical limit. And now I'm going to show you a chart of atmospheric losses, and we'll go through it in detail. First, there's oxygen, and you can see there are some extreme molecular absorption peaks at 60 and 119 gigahertz, which must be avoided by design. Rain is the most significant concern in operational links, and the losses will depend on the rain rate, the altitude of the rain cloud columns, and the size of the rain droplets. In clear weather, there is of course no effect, and in light rain or drizzle, only the highest frequencies will have significant losses. In heavy rainstorms, however, only frequencies below 10 gigahertz will make it through the atmosphere with negligible losses, and higher frequency links can be completely blocked. This is caused by Mie scattering. When electromagnetic waves pass through much smaller particles, such as molecular water and oxygen, there is minimal scattering. Somewhat larger particles, like liquid water droplets in clouds, will have broader absorption and can create Rayleigh scattering, but at RF frequencies, Rayleigh scattering is somewhat minimal. So the significant term is Mie scattering, which occurs when the particle diameter, in this case millimeter scale rain droplets, are similar in size to the wavelength. Consequently, compared to rain, both water vapor and clouds absorb much less RF energy because these particles are much smaller than even millimeter wave wavelengths. However, in very dense clouds and saturated humidity, the effects can be significant at higher frequencies. In most cases, losses from aerosols and other particles are minimal. And one more factor is scintillation, which most significantly affects very low frequency radio waves over a fairly small bandwidth range. The bandwidth is also legally constrained. Different types of terrestrial communications, military SATCOM, and space-based radar take up significant portions of the FCC bandwidth allocations, so both practically and legally speaking, there's only a total of around 50 gigahertz allocated to SATCOM, which is then split between uplink and downlink. As you can see here, the bands generally avoid the highest oxygen absorption regions, and Starlink version 3 uses practically all the available bandwidth. Or so I thought. As I was creating this video, SpaceX filed their application for the 100,000 satellite Gen 3 Starlink constellation, which would probably be called V4 since Gen 2 is called V3. The only major change is the addition of the so-called D-band millimeter wave frequencies. These span from 122 to 275 gigahertz and would add up to 127 gigahertz of backhaul bandwidth to the Starlink system. In this frequency range, the rain attenuation remains high, but levels off as the millimeter waves become smaller than rain particles and closer to the size of cloud and fog particles. And this gradually causes more Rayleigh scattering and liquid water absorption. The gaseous molecular absorption of water gradually rises as well and spikes at 183 gigahertz and 325 gigahertz. So this makes the losses from humidity considerably higher. The overall losses are very high, but they can be overcome with much higher gain antennas in clear weather. Here I've added in all of these Starlink D-band links into my link budget simulator, and this is all based on the FCC filings, so all of these gains and power settings should be about right. And you can see that these have sufficient signal-to-noise ratio to achieve fairly high spectral efficiency, so around 8 bits per hertz in this case. And you'll also notice that they're using a very low amount of power, considering that they're using an extreme amount of bandwidth, so 43,000 megahertz just on this one portion of the link here. And the reason for this is that the gain of both the transmitter and receiver is so much higher, and so they can afford to use less power even over this range. The sensitivity to rain is somewhat higher than in the other backhaul links. However, you can see in even somewhat rainy conditions, it can still somewhat function because they have so much margin built into that link budget. If you add up the data rates from all of these links, it comes out to 2 terabits per second, and that's just for a single link between a satellite and a ground station. And that's really impressive because you could do all of this with a single parabolic antenna. And the existing Starlink V3 design has 4 parabolic antennas, and even then they're only getting 1.2 terabits of total backhaul capacity. The semiconductor industry has only recently advanced far enough to create efficient amplifiers and other electronics for millimeter wave RF. So that limits the amplifiers to operating at low power. However, because the antennas are such high gain, the link budget remains fairly good. At above 300 gigahertz, however, the microwave spectrum ends and the far infrared range begins, and we do not yet have the technology to efficiently or economically use this bandwidth. So even if we could hypothetically use 200 gigahertz of bandwidth over the entire microwave spectrum, our data rate still caps out at around 4.8 terabits for a single link between 2 locations. The obvious solution is to simply connect your satellite to many different ground stations, multiplying your data rate with more parallel lanes. However, we do have another option that could give us unimaginable serialized throughput, and that will be the topic of today's video: laser links between the Earth and space. In particular, we will analyze Blue Origin's recently announced TeraWave constellation, which aims to create 6 terabit laser links through the atmosphere between user ground stations and medium Earth orbit satellites. Unlike microwaves, which have carrier frequencies in the gigahertz range, shortwave infrared, near-infrared, and visible light oscillate at hundreds of terahertz. Therefore, in a single link, you can occupy several terahertz of bandwidth, and even at poor spectral efficiency, this can provide much higher data rates than what is physically possible with the entire RF spectrum. Because of this advantage, optical and infrared communications have already taken over many applications in the form of optical fiber cables and space laser links. To start, we will cover the basics of optical communications and communications in general. The point of any communication system is to transfer data from an application on one computer to an application on another specific computer. In most cases, the data must also be compressed, encrypted, and error-free. To achieve this, we use several layers of communication standards. Most internet traffic uses HTTPS and TLS at the application layer, which authenticates servers and encrypts the data so that it cannot be intercepted in transit. Data is often compressed at the application layer as well. Next, TCP or QUIC transport protocols ensure that all of the data arrives error-free in the correct order. Pure UDP is used in cases like video streaming and gaming, where speed is more important than perfect data integrity. Internet Protocol IP gives addressing for routers to optimize and connect the many links between devices. At each of these layer transitions, metadata is added or stripped off from the original data. There's more diversity in the protocols for the data links between all of the devices and routers in the chain of communication. 5G, Wi-Fi, Ethernet, and proprietary Starlink protocols will all encode data differently. And within each protocol, there are multiple Layer 1 options for how to modulate the physical signal. In optical and electrical communications, the most common modulation scheme is pulse amplitude modulation, or PAM. You can also encode information in pulses by varying the timing, pulse position modulation, and duration, pulse width modulation. However, the most common scheme is varying the intensity, pulse amplitude modulation. PAM2 represents 1 bit per symbol, and this is also called non-return to zero, or in some cases return to zero, if the signal returns to zero between pulses. Likewise, PAM3 has 3 levels, PAM4 has 4 levels, and so on. Real signals have smooth transitions instead of being perfect square waves, but I'll sometimes show the ideal transitions for simplicity. In polar PAM, the signal oscillates between positive and negative voltages, which is why it can be called alternating current despite having no AC carrier sine wave. Some copper cables use passband, which modulates signals onto an AC carrier wave, like in RF, but most standards are baseband, meaning they directly adjust and measure pulses of direct current voltage. Here I plot an amplitude shift keying signal that's passband that could be used on an antenna versus a pulse amplitude modulation baseband signal so you can see the difference. For PAM and optical communications, the instantaneous voltage of the optical carrier wave cannot be directly measured. Instead, the average power from a photodiode is measured as an absolute value. So for 2 levels, it is unipolar NRZ between 0 and a maximum level, also called on-off keying. And while the optical power envelope is measured as a square wave, there is an extremely high frequency optical carrier wave with an oscillating voltage present underneath. In these demos, I usually show a fractional bandwidth of around 20%, meaning 5 carrier oscillations per symbol. This is near the practical limit for most RF antennas and amplifiers, but keep in mind that in most real-life systems, the carrier will usually oscillate hundreds or thousands of times per symbol because the carrier frequency is much higher than the bandwidth or symbol rate. This is especially true for optical carriers in the hundreds of terahertz range. Differential coding schemes like NRZI are another common and useful modulation type. Instead of coding 1s and 0s as absolute amplitude levels, a 1 can invert the signal and a 0 can keep the signal the same. Higher order modulations, like PAM4, can also be differential. In this case, since there are 4 absolute levels, there are also 3 different options for changing the level and 1 option to remain at the same level, so the bit rate is the same as absolute PAM4. PAM signals are often plotted on eye diagrams. These are created by overlaying hundreds or thousands of symbols on top of one another to judge the quality of the overall signal. Here I simulate 1,000 symbols, and as I increase noise, clock desynchronization, transition time, and other factors, there are distinct changes to the eye diagram that can be used to diagnose problems. One problem with PAM, even differential PAM, is that long strings of the same symbol can cause the transmit and receive clocks to lose synchronization. Sensors and other electrical components can also malfunction with continuous DC current building up charge from repetitive symbols. An early solution to this problem was Manchester coding, which encodes 0 as pulsing on then off and 1 as pulsing off then on. This scheme doubles the bandwidth for the same bit rate, but the advantage is that for a long string of 0s or 1s, where there would previously be a constant direct current, for Manchester coding, it will alternate to synchronize the clock and balance the positive and negative voltages like an AC sine wave. However, doubling the bandwidth is an unacceptable trade-off, so modern standards use much more efficient coding schemes to accomplish the same functions, along with built-in error detection and/or error correction. As an example, I will show you how the coding protocol works for 100 gigabit Ethernet. Ethernet is the most common communication standard for copper and fiber cables, and there are multiple standards at each data rate depending on the cable type, distance, and the number of parallel lanes. Ethernet frames are thousands of bits long, and they contain a preamble, which marks the start of the frame, MAC addresses for switching, and a 32-bit frame check sequence based on the rest of the frame. The frame check is a checksum long enough that it is virtually impossible, roughly 1 over 2 to the power of 32 odds, for it to not detect an error within the frame. The data and metadata are first chunked into 64-bit blocks with 2 header bits, which is a 64B 66B line code. Afterwards, the block passes through a scrambler using XOR operations with previous bits. The purpose of the scrambler is to modify cases of long strings of the same symbol into sequences with plenty of state changes and balanced voltage levels, like in Manchester coding. Next, 4 66-bit blocks are transcoded, meaning the 8 header bits are compressed into 1, which saves a few percentage points in overhead. This becomes a 256B, 257B block and is the full line code name. Next is forward error correction, which includes parity bits along with the original message that allow for corrections to errors within either the message or the parity bits. In this case, the protocol uses Reed-Solomon 544-514. It is numbered as such because 20 of the 257-bit blocks are combined into 5,140 bits, which are then sliced into 514 10-bit finite field elements. This means each 10-bit symbol represents one of the 1,024 possible order 9 polynomials with 0 or 1 as coefficients. Those symbols become coefficients of an order 543 polynomial with 30 empty symbols added on to the end. Next, the message polynomial is divided by a generator sequence, which is known by the transmitter and receiver. The remainder of the division is then combined and sent along with the original message as 544 total symbols called the code word. When the combined message arrives, the same division by the generator is done on the combined message, and if the remainder, which is called the syndrome, is 0, then there are no errors. If the remainder is not 0, it means there is an error, and there is a multi-step process to use the syndrome to find and correct the erroneous symbols. I will skip that explanation for now, but there are other videos about Reed-Solomon decoding on YouTube if you are interested. At this code rate of 94.5%, which is pretty high, the error correction will work perfectly until the number of erroneous 10-bit symbols is greater than 15, and the error detection will work perfectly up to 30. However, this means you could correct up to 150 bit errors in a row, assuming they are contained within 15 symbols, and this makes Reed-Solomon very effective for burst errors. There are many different types of forward error correction, and they all have different trade-offs. These include random versus burst error performance, code rate overhead, compute, memory, and latency, and the coding gain, which is the signal-to-noise ratio improvement at the same bit error rate versus no forward error correction. In this case, they chose a high code rate Reed-Solomon to optimize latency at the expense of some coding gain and added complexity, and the rationale is shown on the screen here. For some use cases, the signal-to-noise ratio is high enough that forward error correction is not needed, and the system can use only the frame check error detection and retransmit lost packets with the higher level communications protocols. The important concept to remember is that forward error correction can massively improve your bit error rate at the cost of some data rate and processing. The final trade-offs in coding are the modulation type, baud rate, and parallelization. Unlike in RF communications, there are no hard limits on parallelization since you can run many fibers in parallel, and the bandwidth of lanes can exceed 100 GHz. For that reason, low spectral efficiency is acceptable, and 100 gigabit Ethernet only uses up to PAM4 for its modulation. Both NRZ and PAM4 are used, and the trade-off is that PAM4 requires a higher signal-to-noise ratio, as well as various other hardware requirements to achieve the same bit error rate as NRZ. However, with PAM4, you can use half the bandwidth or half the number of lanes as with NRZ at the same data rate. Higher baud rates allow for higher data rates and more serialization, but they require more advanced electronics to process. Just as with spectral efficiency, there are diminishing returns as you go higher in baud rate, and commercial copper and optical transceivers typically max out at around 100 gigabaud with our current technology. In general, there is an ongoing trend to transmit more data across fewer lanes to make the system more serialized. This is intuitive since if you have more parallel lanes, then you need to buy more cables and transceivers and electronics for each additional lane. The downside is that those fewer transceivers need to be higher tech and more expensive. Another issue is that eventually you need to deserialize all of that data. CPUs and GPUs cannot clock at 100 GHz, so for a 200 gigabit Ethernet lane, you need to use more advanced SerDes to convert up and down from the single digits gigahertz binary signals of computer transistors, and this adds cost and latency. Moving on to the Ethernet cable types, you can see on this chart that the short ranges use copper only in the form of traces on PCBs in different kinds of copper cables. Copper is preferable for short distances because computers natively use electrical signals, so with copper cables, there is no optical to electrical conversion required. However, beyond a few meters, the electrical resistance of copper is not acceptable for modern high bandwidth standards. This is because the electrical resistance and noise is very high when transmitting a very high bandwidth signal. As we discussed in my power transmission video, even 60 Hz alternating current produces a skin effect where the effective resistance increases due to the current concentration near the edge of the cable. For a 100 gigabaud copper cable, the effect is even more extreme. Dielectric losses and various sources of noise and distortion also increase with your symbol frequency. For a real-world example, the NVIDIA NVL72 data center rack uses a backplane of copper cables for all of the scale-up NVLink switches to connect the GPUs within the rack. Then it uses optical fiber cables for the Ethernet network switches to connect to other racks across the data center. Parallelizing copper is currently much easier than optical, and because they can use so many more lanes, the scale-up bandwidth with copper is 20 times higher than the optical scale-out network bandwidth. That extreme bandwidth on copper is the real magic behind the much better performance of rack-scale data centers versus small clusters or individual GPUs. The next generations of NVIDIA GPU racks will go even crazier with their connectivity technology. Rubin, coming out later this year, will use the same number of copper NVLink lanes and still use PAM4 at the same baud rate, but it will operate each copper lane in full duplex, sending signals in both directions at the same time. This requires bidirectional SerDes and analog and/or digital self-cancellation of the transmitted signal on either end. Bidirectional lanes are possible with optical fiber, but since fiber lanes are very small and light and cheap compared to copper, they are usually only operated in one direction each to save on complexity of the transceivers, where most of the cost is. On the networking side, Rubin will also double bandwidth over Blackwell. Feynman, likely coming out in 2028, will double the GPUs per rack to 144, connect those with some mix of copper or optical lanes, then connect all of the switches of 8 racks with optical NVLink lanes, combining 1,152 GPUs into a single domain. And it will also likely double networking bandwidth again over Rubin. Optical fibers can be split into two main categories: multi-mode fiber and single-mode fiber, with multi-mode used for short distances and single-mode used for longer distances. Single-mode fibers are smaller and transmit a signal with a single transverse mode of light, while multi-mode fibers transmit the signal on multiple modes. Transverse optical modes are electromagnetic field patterns of photons that the optical field will produce. In fiber optics and lasers, light will be described using these field patterns instead of individual rays or photons. The optical field has a transverse mode and also a longitudinal mode, which corresponds to a wavelength and frequency. A single mode fiber is small enough that only the fundamental mode of light will be guided and propagate, while the higher order modes will escape into the surrounding cladding and dissipate. For a wider fiber, or for a laser propagating through free space, higher order modes will propagate along with the first mode. Higher order modes result in greater diffraction in free space, and this is why the optics and laser sources in laser terminals and laser weapons measure their beam quality relative to an ideal single-mode Gaussian beam with the m-squared beam quality factor. Do not confuse multimode fiber with wavelength division multiplexing, in which multiple channels of light are sent with different frequencies on the same optical fiber. MMF fibers usually still transmit just one signal per fiber. Wavelength division multiplexing is much more common in very long distance, high capacity single mode fibers such as undersea cables. In a step index multimode fiber, meaning the fiber has a consistent refractive index, the higher order modes will travel a longer distance than the first mode, which creates a delay in the arrival time between modes and stretches the transitions between levels. At some distance, this will make the MMF fiber unusable. The most effective mitigation of this is to use graded index multimode fibers, where the outer shells of the fiber have lower refractive index and allow the higher order modes to propagate at the same average speed as the first order. However, just like chromatic aberration in a lens, it does not work perfectly, and single mode is still superior, achieving faster baud rates and longer distances. Despite its inferiority to single mode fiber, multimode fiber is still much more common at short distances, primarily because it can be operated with less expensive lasers and optics, and we will explain why later in this video. Another trade-off in optical cables is which wavelength of light to use. Multimode fiber typically uses 850 nanometers, and single mode fiber uses a wider range, usually around 1310 nanometers or 1550 nanometers, for for very long distance cables. These wavelengths are also common for laser links in space. Once again, this is due to a trade-off between performance and transceiver costs. 850 nanometer lasers are cheapest and used for short distances, where the attenuation per unit of distance can be much higher. The lower attenuation wavelengths are used with more exotic and expensive transceivers. Some emerging innovations in fiber cables are hollow fiber cables, which use air instead of glass as the propagation medium, and multi-core fiber, which packs a greater number of threads into the same outer cladding. Now let's move into the options for optical modulation. The simplest is direct modulation, where the current of the laser diode is adjusted to create pulses of varying intensity or to turn the laser on and off. This contrasts external modulation, where the laser is operated as a continuous wave, and an external modulator modulates the amplitude or phase outside of the laser diode. External modulation has better performance and is used for higher data rates and longer ranges. The disadvantage of direct modulation is that laser pulses have a slow ramp-up of intensity that limits bandwidth, and the pulses produce an unintended frequency distortion known as chirp. Let's review the basics of lasers and semiconductors to explain why this happens. The typical explanation of lasers involves a crystal or glass fiber gain medium that is surrounded by other lasers or light sources that act as an optical pump. This is correct for high-power laser weapons. However, most lasers, including optical communications lasers, use only semiconductor laser diodes. So here we'll do a review of semiconductors. In chemistry, we arrange the periodic table based on the number of valence electrons within atoms. Valence electrons are the outermost layer of electrons that interact with other atoms. As electrons are added, they form into probabilistic subshells, starting with a spherical S subshell and then a P subshell with orbitals along each axis. The rows on the periodic table are the periods, which represent the number of shells, and the columns are families, which represent the number of valence electrons. The exceptions to this pattern are hydrogen and helium, which have a shell with only one spherical subshell, and the transition metals that add electrons below the outermost shell in a D subshell. When we get out to neon, there are 8 valence electrons, which makes all of the shells full, and this is why it will rarely react with other atoms and molecules. The same is true for all the other noble gases with full outer shells. When we add an electron and proton to a full shell, a new shell is created, and the atom becomes a reactive alkaline metal like sodium or potassium. You can also form highly stable molecules, which are combinations of atoms that result in filled valence electron shells. For example, when you combine pure sodium with 1 valence electron and chlorine with 7 valence electrons, the two very reactive substances react and form a very stable salt crystal where the shell of each atom is filled by sodium sharing electrons with its chlorine neighbors. Common semiconductors are also stable crystals. The most common is crystalline silicon. Silicon has 4 valence electrons, so when combined into a crystal, it shares 1 electron with 4 other silicon atoms to fill all of the shells. The same is true for diamonds, using the valence electrons of carbon or silicon carbide, mixing together silicon and carbon. Many semiconductors will combine a group 3 atom, such as gallium, with a group 5 atom, like nitrogen or arsenic, to form stable crystals like gallium nitride and gallium arsenide. And these are called compound semiconductors. The subshells of individual atoms are described as discrete electron energy states. When the atom is in an excited energy state, an electron can occupy higher energy levels. When combined into a crystal, the electrons are shared between atoms, and the electrons cannot share discrete quantum states with the same spin and energy and orientation. So the electrons occupy a wider continuum of energy states called energy bands. The highest energy nearly filled band is called the valence band, beyond which is the nearly empty conduction band. The difference between these energy bands is the band gap, and electrons cannot occupy energy states within this gap. Any semiconductor above absolute zero temperature will have electrons in the conduction band that can move freely throughout the crystal, and they will leave behind holes which can also move throughout the crystal. Within the conduction band, electrons can return to lower energy states by recombining with a hole in the valence band and releasing a photon, which is the principle of light-emitting diodes. Photodiodes measure the inverse, where photons excite the semiconductor and create electron-hole pairs. Beyond the conduction band is the vacuum level. If an electron reaches a higher energy than the vacuum level, it will be released from the semiconductor, ionizing the remaining material. These energy band thresholds determine the behavior of a semiconductor. For example, the wavelength of light is inversely proportional to the energy of photons, so the thresholds of these bands determine the emitting color of light-emitting diodes and the color sensitivity of photodiodes. Conductors differ from semiconductors and insulators in that they have no band gap and their energy bands are partially filled or overlapping. Insulators generally have a wider band gap than semiconductors. However, a wide band gap material such as diamond is still considered a semiconductor because it can be doped with impurities and used for semiconductor devices. In doping, small quantities of group 3 or group 5 atoms are deposited into the crystal structure. Group 5 dopants, like arsenic, are called donors since they donate an extra valence electron to the structure. Group 3 dopants are called acceptors since they accept a valence electron and introduce a hole into the structure. Semiconductors doped with acceptors are called p-type since they carry positive charges with holes, and semiconductors doped with donors are called n-type since they carry negative charges with free electrons. Semiconductor devices are defined by how the p and n doped semiconductors are arranged. In optical communications, we are primarily concerned with different types of diodes. Diodes generally allow current to flow in only one direction, and they do not have a gate to control the flow. Most diodes are semiconductor devices with a single p-n junction. When the p and n doped semiconductors meet, the free electrons in the n-type recombine with the holes in the p-type and vice versa, forming a depletion zone with fewer charge carriers. The dopants that are left behind without their nearby electrons or holes become ions that produce an electric field that opposes the further diffusion of charge carriers. And charge carriers meaning either electrons or holes. When you apply a positive voltage P to N, the electric field is opposed, the depletion zone is narrowed, and charge carriers can pass through the diode. While current is flowing, the free electrons continually recombine with the holes and emit photons or heat. Indirect bandgap semiconductors like silicon produce very few photons, so LEDs use direct bandgap compound semiconductors that efficiently produce photons during recombination. The produced wavelength of light is dependent on the bandgap of the material. So to produce specific wavelengths of light, the semiconductors can be mixed into alloys to create a specific bandgap, and these will have more than 2 elements listed in their name. You can see on this chart that the blue and green LEDs use the same type of alloy, and in that case, they just use different ratios of indium to gallium to change the bandgap. Photodiodes are the inverse of LEDs, and the layout is roughly the same. When incident photons have more energy than the semiconductor bandgap, electrons will be excited from the valence band to the conduction band. This creates an electron-hole pair, which is then separated by the electric field, producing a voltage across the cell. Photodiode sensors are often operated with a reverse bias voltage to widen the depletion region and strengthen the electric field. Unlike in LEDs, indirect bandgap semiconductors like silicon can be used. In fact, crystalline silicon is one of the best semiconductors for photovoltaic cells in solar panels. CMOS camera photodiodes also use silicon underneath little color filters. Without the filters, the sensors can easily sense near-infrared light. However, to see further into the infrared range, you need more exotic semiconductors, which is one reason why infrared cameras are more expensive. Photodiodes for optical transceiver detectors prioritize baud rate, so they typically use PIN diodes with an undoped intrinsic layer. This results in a wider depletion region and lower capacitance, which improves performance. Also note that the photodiode is not measuring the voltage of the optical field of the light wave. Instead, it is measuring photoelectrons for a given range of frequencies, which can be converted into an average intensity measurement. The discrete quantum nature of photons requires them to be absorbed at some probabilistic random time. When the rate of photons arriving at the photodiode is very low, say on average 5 photons per measured bit, this results in a varying number of photons being absorbed at any given time period. This produces a varying measurement of average intensity called shot noise, and this is often the primary noise concern in both optical imaging and space laser links. Laser diodes use a slightly different design to achieve the properties of lasers, those being a more narrow range of frequencies, coherent or stable phase, and a somewhat directional beam. They usually take the basic form of a PIN diode, where an undoped intrinsic or I layer is used as the gain medium for stimulated emission within the laser. A common choice for this layer is a quantum well, which is a very thin layer of a lower bandgap undoped semiconductor sandwiched between two higher bandgap semiconductors that traps holes and electrons and makes recombination and photon emission much more likely. In a standard LED, the photons are spontaneously emitted in a random direction and phase when electrons and holes are recombined. The energy varies slightly from the bandgap energy because the electrons and holes have energies within the somewhat wide valence and conduction bands, so the wavelength is a broader range. In stimulated emission in laser diodes, a photon within the optical cavity will stimulate the recombination of the electron and hole, and the generated photon will match the energy, wavelength, phase, polarization, and direction of the existing photon. The generated photons will stimulate the emission of more photons with the same characteristics as they bounce back and forth within the optical cavity, and some fraction of these photons will pass through the output coupler as a coherent laser beam. Specific types of laser diodes limit the range of frequencies and optical modes in different ways. Vertical cavity surface emitting laser, VCSEL diodes, are used for short distance multimode fiber. In these designs, the optical cavity and emitted laser is perpendicular to the semiconductor layers. This differs from the parallel optical cavity in edge emitting lasers. VCSELs typically use gallium arsenide in the quantum well emission layer, which produces 850 nanometer near-infrared light. On either side of the cavity, there are distributed Bragg reflectors, which are mirrors made from alternating layers of semiconductors with differing refractive indices. Photons can be reflected at each of these layers, and it results in very high reflectivity. The top mirror is less reflective and acts as the output coupler that allows the light to pass through. The round-trip optical path length of the cavity, which is the actual length times refractive index, is set to match an integer product of a desired free space wavelength, usually 850 nanometers. This produces a resonant constructive interference for that specific wavelength. To demonstrate, you can see that at the resonant frequency, the wave will always arrive back to the gain medium where it started its cycle, and therefore the stimulated photons will constructively interfere and accumulate coherently. When the wavelength is not resonant, such as 879 nanometers shown here, stimulated photons destructively interfere since they do not arrive at the gain medium at the same phase in every cycle. You can already see the effect with only a few bounces, but if I show 1000 round trips, you can see that nearly every other frequency will not last long within the optical cavity. You can see that there are other integer factors that would resonate with this exact path length. However, these are not closely spaced because of the short vertical cavity, and they cannot be emitted by the gallium arsenide gain medium because its band gap produces a narrow gain region around 850 nanometers. Furthermore, the path length of the cavity is not a single value because the light is reflected as an optical field at every layer of the Bragg reflector at the same time. This is not an issue for the 850 nanometer light because the optical path length of the layers of the Bragg reflector are exactly 1/4 of 850 nanometers, and every other surface is a low to high refractive index transition that gives a 180-degree phase shift. Therefore, any round trip through a Bragg reflector will result in an integer of a wavelength spatial shift, which means there is no phase offset between layers, and this will produce a successful reflection. This coherently reflectable wavelength is called the Bragg wavelength. For other wavelengths, since there is a phase offset depending on which layer they reflect at, there is a destructive interference in the reflective wave. In other words, these wavelengths mostly pass through the Bragg reflector without reflecting, and this is another layer of wavelength selection. This system results in a narrow wavelength and frequency range, and this is called the line width in the context of lasers. However, the line width and other performance metrics of VCSELs are poor compared to other edge-emitting laser diodes. The size of the oxide aperture is another important factor in VCSEL performance. This is a semiconductor layer containing aluminum that will be oxidized inwards, leaving an unoxidized opening in the center. The oxidized portion is insulative, so the current passes through the small opening, and the optical properties of the oxide layer guide the light into the smaller aperture as well. A smaller aperture results in lower order transverse modes, and to create a single mode VCSEL for a 9 micron single mode fiber core, the aperture must be below 4 microns in diameter. However, a wider aperture results in lower resistance and much higher power, so the majority of VCSELs are manufactured with wider apertures for use with multimode fiber. The vertical layering of the VCSEL makes manufacturing and testing simple and inexpensive, especially for wide aperture VCSELs, so these are the most common choice for short distance MMF. The short active region also allows the photon population to react very quickly at low currents with direct modulation. Returning to the problems with direct modulation, let's look at what happens as the current applied to the VCSEL diode changes. When the current increases, the fluctuation in carrier density produces an optical gain spike, which causes an overshoot in the average power. The carrier density also changes the refractive index, which changes the cavity's optical distance and resonant frequency, and this is the cause of the chirp. All of these problems are manageable for low baud rates, PAM2, and short distances. However, for high data rate, medium and long distance single mode fiber, we need the improved performance of edge emitting lasers and external modulation. The most basic edge emitting laser is called a Fabry-Perot laser, which has a basic laser diode design where the laser emits in parallel to the semiconductor layers. The reflectors are placed perpendicular to the other layers on either side. This design relies on the optical length of the cavity to select the wavelength. However, since the optical cavity is so long, usually hundreds of times longer than a VCSEL, there can be multiple closely spaced resonant frequencies that will laze at the same time. However, the field can be efficiently confined into a single transverse mode by limiting the lateral width of the emitting region. An improvement on FP lasers is the distributed feedback laser, or DFB. The key difference is that instead of using reflectors on either side of the diode, a distributed Bragg grating, which uses the same principle as a Bragg reflector, is arranged parallel along the length of the emitting region. Just as in the FP diode, the optical cavity is hundreds of times longer than a VCSEL. So these diagrams are not to scale, and DFBs actually have hundreds or thousands of Bragg grating periods. In the center of the grating, there is usually a skipped transition that produces an extra quarter wavelength phase shift, which is included to prevent a coupling effect that produces dual lasing wavelengths. If you think of the light as rays, the Bragg grating is not very intuitive since there are no Bragg reflectors embedded within the quantum wells. So keep in mind that this grating is interacting with the entire electromagnetic field of light within the optical cavity, and it is able to cause reflection as if the grating existed at every vertical layer. Just as in a VCSEL, only the optical field with the Bragg wavelength will be coherently reflected by the Bragg grating. The other closely spaced longitudinal modes that match the Fabry-Perot distance will be phase shifted incoherently by the Bragg grating, destructively interfere, and therefore not reflect and amplify within the optical cavity. This system results in a much narrower line width compared to VCSELs. The quantum well semiconductor in DFBs is often indium gallium arsenide phosphide, and this alloy can be tuned for 1310 or 1550 nanometers or something in between. The trade-off in these wavelengths is that 1550 is the absolute lowest attenuation in glass fiber, while 1310 is the lowest chromatic dispersion. 1310 nanometers is an inflection point in the refractive index, so all the wavelengths near 1310 have very low chromatic dispersion. At 850 or 1550, where the gradient is steeper, slightly different wavelengths will disperse over long distances and distort the signal. So the trade-off is signal-to-noise ratio versus distortion, and it favors 1310 at medium distances and 1550 at long distances, especially with narrower line-width lasers and digital signal processing to filter out the predictable distortion. DFB lasers can be directly or externally modulated, and they are most common for high data rate, medium distance, single-mode fiber links. Distributed Bragg reflector (DBR) laser diodes are used for the longest distances and highest performing links, such as undersea cables. These are also edge-emitting lasers and have a very similar design to DFB. The difference is that in a DBR laser, the active emitting section and reflective grating sections are separate. This allows for maximum tunability since each section can have the current and temperature adjusted independently. Tuning the wavelength is helpful for dense wavelength division multiplexing, as in undersea cables, because you do not need to design a new diode for each of the dozens of channels sharing a fiber. These often have long passive cavities, phase tuning sections, and more complex control systems that can achieve better line width and other performance metrics, but at a higher cost. Some laser diodes will have a semiconductor optical amplifier, or SOA, attached. These act as an extra gain region with minimal reflections, where the light only passes through once. This enables adjustment of the power output of the laser without messing with the resonant wavelength and other characteristics of the optical cavity. SOAs can also be used as modulators, although the performance is not as great as other choices. For amplification in undersea cables, they space dozens of erbium-doped fiber amplifiers, EDFAs, along the route to keep the signal power high. As in the semiconductor optical amplifier, there are no reflectors so that they can amplify dozens of wavelengths at the same time for dense wavelength division multiplexing in the C and L bands. Reflections are prevented with optical isolators, and the pumped light is combined and filtered out at either end of the amplifier fiber with couplers. If there were reflections, that would become a fiber laser, which would produce its own unwanted signal. Fiber lasers are common for high-power laser weapons, and in those designs, the glass is doped with ytterbium, still pumped with wavelengths around 980 nanometers, but outputting a 1070 nanometer laser. Amplifiers are typically placed just after the transmitter or periodically along a fiber route, but they can also be placed just before the receiver as an optical preamplifier. These accomplish the same function as low-noise amplifiers and antennas. They amplify the signal to the level needed for electronics, but they cannot recover a poor quality signal that has already been lost in noise, and that includes very weak signals with excessive shot noise. Now let's move on to external modulation, where a continuous wave laser is modulated outside of the laser diode. The most common choice for external modulation is the electro-absorption modulator, which modulates the amplitude through absorption. The design resembles the inverse of a semiconductor optical amplifier. By operating at a reverse bias instead of a forward bias, it can adjust its absorption based on the voltage applied. The semiconductor in the active region is often the same type of alloy as a laser diode or amplifier diode, but with a slightly higher band gap so that it is transparent at its lowest reverse bias setting, but still close to the absorption edge. The refractive index and temperature change with absorption, so it is not chirp-free, but the chirp is much lower than in direct modulation. Next is the pure phase modulator. These devices apply an electric field to an electro-optic crystal, such as lithium niobate, which changes the refractive index and optical path length, shifting the phase. This is known as the Pockels effect. Since these need to shift a 1.55 micron wavelength by up to 180 degrees, and the refractive index change is only a small fraction of a percent, they need to span several centimeters. This is very long compared to most semiconductor devices, and it makes conventional lithium niobate bulk crystal devices very expensive. An emerging technology is thin film lithium niobate. The more compact form factor allows for higher electric field strength and refractive index change at the same voltage. This results in a smaller device, better efficiency, and faster bandwidth, often well over 100 gigahertz. Gallium arsenide is less common for fiber, but it is an alternate choice for space laser links because of its thermal and radiation properties. Indium phosphate uses different electro-optic effects, and it is a more mature technology that also achieves extremely high baud rates and efficiency. Finally, there are silicon photonic phase modulators. Crystalline silicon does not produce a strong Pockels effect or other similar electro-optical effect, so the design usually requires using a p-n junction to change charge carrier density, which then changes the refractive index. Silicon does not have the maximum performance, but it is attractive for manufacturability and for integration with computers in co-packaged optics and data center optical networking. A recent breakthrough in silicon photonics is the mass production of microring modulators. These are tiny circular waveguides with a resonant frequency that changes based on the refractive index via the applied voltage. When connected to a straight waveguide, the microring will couple with the resonant frequency and redirect it from the waveguide. At certain resonant frequency offsets, microrings can also produce a phase shift, so these can be used as either amplitude modulators or phase modulators. Another modulator with this ability is the nested Mach-Zehnder modulator. But before we show those, we need to cover IQ modulation, meaning in-phase and quadrature modulation, and coherent detection. For a single carrier wave, amplitude modulation can only produce a phase shift of exactly 180 degrees by inverting the signal between a positive and negative voltage. To create other phase shifts, two carrier waves with a 90-degree phase shift, an in-phase cosine, and quadrature sine are interfered. And by altering only the amplitude of the two carrier waves, you can create many phase and amplitude options for a combined quadrature amplitude modulation signal. So for IQ modulation, we use constellation plots instead of eye diagrams since we are considering both phase and amplitude. When you plot the in-phase component on the x-axis and quadrature component on the y-axis, the phase is the angle from the positive in-phase component and the amplitude is the distance from the center. Each symbol will then have a unique combination of phase and amplitude. 16 QAM and 16 APSK will have 4 bits per symbol, 32 QAM has 5, 64 QAM has 6, and so on. Likewise, when an incoming signal is demodulated, it will be mixed with both in-phase and quadrature carrier waves to recover the carrier phase and amplitude. This is called coherent detection. For RF demodulation, the local oscillator needs to be in sync with the transmitter's carrier wave. If there is a 90-degree or 180-degree phase error on a symmetrical constellation like QPSK, the control system cannot simply correct it. To prevent this ambiguous phase, communication standards will include recognizable pilot sequences that the system can lock onto. Alternatively, instead of directly encoding a phase, the system will encode the bit with differential phase shifts and/or differential amplitude shifts. This is how coherent modulation works for RF. But for optical, it is not as simple, mainly because it is physically impossible to directly measure the instantaneous field voltage of an optical wave. For microwaves, an antenna converts the RF wave into an electrical AC voltage, and the higher frequency carrier can be downconverted so that the instantaneous positive and negative baseband voltages can be sampled with an analog to digital converter. For optical sensors, they interact with electromagnetic waves as particles. Instead of measuring an AC voltage from an antenna, they only output an average power value that can only be a positive number. So the optical carrier cannot be electrically downconverted into a baseband voltage. Furthermore, the optical sensor cannot sample at hundreds of terahertz anyway. However, it is physically possible to measure and modulate relative phase with optical interferometry. In a Mach-Zehnder interferometer, 2 beams of light are interfered before they ever reach an optical sensor or a transceiver output fiber. The basic design divides a beam with a 50-50 beam splitter, phase shifting the lower arm by 90 degrees. After the reflection, they arrive at the second beam splitter 90 degrees out of phase. So when half of both beams are phase shifted by 90 degrees again in the second beam splitter, this makes one path combine in phase, constructively interfering, and one path combine 180 degrees out of phase, destructively interfering. You can see that so far, the resulting interference pattern is the same regardless of the input phase, so this is not a functional detector yet. To detect relative phase, we have 2 main options. First is the delay line interferometer. This design shifts one arm by one entire symbol period to interfere the current symbol with the previous symbol. Because we have a very low fractional bandwidth, one symbol period spans thousands of optical carrier periods. At a 100 GHz baud rate and 1550 nanometer light, this amounts to 10 picoseconds and 1 millimeter in a silicon waveguide and a 700,000 degree phase shift. Relying on the noisy previous symbol as a reference works with differential signaling, but is less reliable than the other option, coherent detection. In this setup, the device uses its own stable local oscillator laser as a reference to interfere with the incoming signal. When you phase shift the local oscillator by 90 degrees, you can recover the in-phase and quadrature components to calculate amplitude and phase. In a Mach-Zehnder modulator, phase modulators are placed along each arm. If only one arm is phase shifted, both the phase and amplitude of the output path will change. By moving the phase shifters together, we can change only phase. Likewise, by moving the phase shifters in opposite directions, we can change only amplitude. To produce arbitrary phase and amplitude combinations for QAM, this requires a nested Mach-Zehnder modulator. This uses 2 90-degree phase-shifted MZMs that will modulate only the amplitude of the I and Q channels. These more advanced IQ detectors and modulators are common for long-distance high data rate lines like undersea cables. Now let's move on to space laser links. Optical inter-satellite links are somewhat similar to fiber-based optical communication systems. The key differences are that there is no attenuation or chromatic aberration from glass fiber, no amplifiers in free space, and the beam will spread since it is not confined within a single mode fiber. The beam also needs to be precisely pointed between distant moving satellites. At each end of the link, there is a laser transceiver terminal. This contains the laser and its optics, a telescope to receive the incoming laser, modulation and demodulation electronics, and a pointing acquisition and tracking system. Usually the primary mirror can be shared by both the laser and the receiver telescope. For a network of laser links like Starlink, each satellite also contains switches or routers. At each node, the system will choose the most efficient path for every data packet. It can either send the data to another satellite through the laser links or transmit back down to an Earth gateway through the antennas. The ground stations then connect to the rest of the internet through fiber. The Starlink constellation is arranged in orbital planes at various altitudes, inclinations, and right ascension of the ascending node. Each satellite will have 2 links between the closest satellites within its plane. These distances are usually between 800 and 2,500 kilometers, and there is very little relative motion between these satellites. Using these long-distance links has the advantage of better latency and lower processing demands since there are fewer demodulation and digital processing steps per packet. However, these shells do not form ideal routing pathways. For example, to connect a US data center to an aircraft in the Pacific, multiple cross-plane laser links may be needed to form the shortest route. This is why Starlink V2 Mini uses 3 200 gigabit laser terminals per satellite, one of which is cross-plane. These cross-plane links can be much shorter, often less than 200 kilometers. However, there is much more relative motion between these satellites, and they need to switch when the connected satellite moves out of view. So these links likely require a more advanced pointing system and a dynamic routing system to optimize all of these connections across the constellation. Interestingly, the design for Starlink version 3 has changed to 6 400 gigabit laser links, which adds up to 2.4 terabits. The previous design was planning to use 1 terabit per laser link. That is still 4 times the V2 Mini capacity and double the RF backhaul capacity per satellite. So those extra lasers are probably for more backhaul throughput in regions without ground stations and for external customers and space data centers. This comes from a blog post that SpaceX just released about Starlink V3, and there are a few interesting technical details that I want to go over as a short aside. First of all, they updated the backhaul antenna design to combine all 4 backhaul frequencies onto the same antenna dish, and this adds up to 1.2 terabits of backhaul. Next, they showed that there are only 3 Ku-band antennas versus the 5 on V2 Mini, but of course they are much larger than the last generation. They stated that they supported 2048 beams for downlink and uplink, which is far higher than version 2 Mini, and also settles the frequency division duplexing question. If you do the math, with 1 terabit total, this is only 488 megabits on downlink per beam, which seems way too low even if these are referring to 240 megahertz beams. So I think they probably will still use fewer beams, and this is just showing the maximum capability of their new digital signal processing chips and potentially moving closer to fully digital phased arrays. Also, the fact that they can form 2048 Ku-band beams definitely supports my conclusion that they are still very backhaul limited. If they could use 2 gigahertz at 5 bits per hertz and 2048 beams, that would be 20 terabits. And if that's possible, then the only constraint there is digital signal processing and backhaul. And that is not even including the new V-band or Ka-band user downlink phased arrays shown here. And in the V4 application, they are adding several terabits of D-band backhaul and apparently not adding any other user antennas, so backhaul definitely seems like the bottleneck for now. We'll return to this point when we talk about the 6 terabit space-Earth laser links. They also requested to use an unlimited number of co-frequency beams instead of the arbitrary limitation to 8 from the last generation. And that will definitely be needed if they have 2,000 Ku-band beams per satellite and 100,000 satellites, a total of 200 million across the Earth. With that many beams and that much digital signal processing power, that allows for the multi-beam source localization and other improved beamforming techniques that we talked about in my radar video. The combination of 4 frequencies into the same parabolic antenna is also very interesting for multispectral radar. They also mentioned the real-time beam density adjustment, and that was something we talked about in my other videos. Finally, they mentioned the next-gen direct-to-cell satellites, and it seems like they are making a completely different design for those, since the antenna would be so large that they probably cannot fit the other antennas and electronics like they could in V2 Mini. Now back on the topic of laser links, lasers can be expanded and collimated with lenses or mirrors, and these are described as Gaussian beams, which will contain 86.5% of the power. The M-squared beam quality factor is very low for laser link beams, which makes them near the ideal single-mode diffraction. In the near field, which falls within the Z sub R Rayleigh range, a collimated laser will diverge very little. Likewise, within this range, you can effectively focus a laser like a reverse telescope to converge the beam into a small spot size, and this is how laser weapons function. However, this focusing distance must be smaller than the Rayleigh range. If it is larger, the beam is effectively focused at infinity, and the irradiance is nearly the same as if the beam were collimated and allowed to diverge at the aperture. Just like a telescope achieves better resolution with wider aperture optics, a larger laser aperture results in a smaller laser spot size in both the focused near field and collimated far field. I made a spreadsheet to run the numbers on this using the full equations and standard assumptions for both a laser weapon and a laser link terminal, and you can see the results here. Firstly, the Rayleigh distance is only 3 kilometers for the laser communications terminal, so the near field properties are not that important. For the laser weapon, however, the Rayleigh range is 80 kilometers, and the irradiance gain from focusing is very high, out to about 100 kilometers. So it makes sense that these are focused, even for space laser weapons at potentially over 100 kilometers range. However, for the laser link, since the aperture is so small, focusing does not improve intensity by even 1% beyond 20 kilometers, so this is why these are just collimated. You can see here that the gain is 105 decibels, so this is 10,000 times higher gain than any of the Starlink V4 RF antennas, which is somewhat promising for the space-to-Earth link budget. The downside of such an extreme gain is that you have an extremely narrow beam, only 15 microradians or 1,000th of a degree across. So you need a point and control system that can achieve this same precision at even better stability. Regardless of the distance between satellites, the laser divergence will always be the same, so the pointing system always has the same challenges. Even at 400 kilometers, which is a probable cross-plane Starlink laser link distance, the spot size is only 12 meters across and barely covers a Starlink satellite's extended solar panels. On the other hand, in the military context, since the beam is so narrow and there are not wide side lobes as in antennas, the link is pretty much impossible to jam or intercept, or even to detect. If you are really paranoid about security, you can use quantum key distribution to guarantee no interception, but this is generally considered as extreme overkill and not worth the trouble. So, since we can always use the far-field diffraction math for these ranges, the gain formula is very similar to RF. The difference is the aperture fill factor, the beam quality factor of the transmitter, and the coupling efficiency of the receiver. And that represents the losses along the transition between the telescope and the insertion into a single-mode fiber, and that will only apply to coherent detectors. You could treat these terms as separate losses, but here I'm just including them within gain. The free space path loss and the rest of the Friis equation is the same. For miscellaneous losses, the pointing error and jitter are more significant for laser links, and for Earth-to-space connections, you also need to consider turbulence. These sources of noise are different than in RF communications because the thermal noise dominant at RF wavelengths produces very few shortwave infrared photons. Instead, the largest source of noise will depend on your specific receiver setup, so there is no short formula that you can treat as the total noise. When you have relatively high power, but low power per bit due to a fast baud rate, you will be shot noise limited by the variance in photons. If instead you have a low baud rate and lots of power in photons per bit, but your total power is very low, the low absolute power electrical noise can overpower the weak signal. In heavy atmospheric turbulence in a high scintillation index, you can have high power and high power per bit, but the variance in amplitude will still cause errors. And there are various other noise sources as well. For example, if you attempt to use low baud rates with a coherent detector with a wide line width, the random phase fluctuations of the laser will shift significantly over individual symbol periods and cause phase rotation and phase errors. This is one reason why low data rate deep space links will typically use direct detection. We will do simulations of these later on, but for now we can simply estimate power received and compare this to the published power sensitivity requirements for commercial transceivers. To analyze this, I have another spreadsheet that has lots of commercial off-the-shelf transceiver types with their power sensitivity and other metrics. You can see when I organize these by photons received per bit, which is proportional to power received per bit, that the long-range coherent receivers tend to have better performance than the short-range direct detection receivers. And forward error correction often makes a big difference as well. However, the absolute best sensitivity detectors, which are usually only needed for deep space optical communications, use direct detection in superconducting nanowire single photon detectors with pulse position modulation. You can see here that these can handle extremely low absolute power in the picowatt range, and the photons per bit can be as low as 1 or even lower. One example shown there is the Deep Space Optical Communications payload on NASA's Psyche mission. Traditionally, these types of missions had to use the enormous Deep Space Network ground antennas and large X-band antennas on the spacecraft, but with this mission, they showed higher data rates optically using a 5.1 meter ground telescope and 22 centimeter satellite telescope. Using pulse position modulation generally results in better photon efficiency because a single photon can carry multiple bits of information based on when it arrives, a theoretical maximum of 4 in this 16 ppm example. In higher order PAM or QAM, multiple photons are needed to determine accurate average intensity, and even PAM2 at its theoretical maximum can only achieve 2 bits per recorded photon. The downside is that ppm has lower spectral efficiency. In this example, the data rate is the same 4 bits per symbol in both, but the 16 ppm requires 16 times higher sampling bandwidth. Of course, in the kilohertz and megahertz range, bandwidth is nowhere close to being limited. The higher order ppm, the higher the photon efficiency and lower spectral efficiency. There is no hard limit, and NASA claimed they could get up to 23 bits per photon, or 0.04 photons per bit, with the DSOC setup. And the opposite is true of PAM and QAM, where at higher orders you get very high bandwidth efficiency with many photons per bit. So that is why ppm is good for low data rates, but never used in ultra-high data rate applications. Unfortunately, there are no public specifications for high data rate satellite laser link transceivers, but there are some lower data rate open standards. First is the SDA's Optical Communication Standard. This is intended as a common standard for military satellites to communicate with each other. However, the standard caps out at only 2.2 gigabits. Likewise, the CCSDS standard is not very ambitious at a 20 gigabit max data rate. So the better approach for now seems to be to use existing telecom standards designed for fiber or to use optimized proprietary standards. Now we will do a rough estimate on the power received in the SpaceX laser terminals. The 10 centimeter aperture is a widely cited value derived from images, and the beam quality and 1 watt transmitter power assumptions are reasonable standard values. Other losses we will set to 1 for now. Plugging all of this into the Friis equation, at 2,000 kilometers we get minus 25.5 decibel milliwatts. And 2,000 kilometers was our estimated high end of coplanar distance between satellites. At 800 kilometers, a reasonable cross-plane link distance, and also a reasonable slant range to a ground station before atmospheric losses, we get minus 17.6 dBm. At the absolute maximum low Earth orbit laser link range of 5,000 kilometers, it's minus 33.5. This is the maximum because for a 500 kilometer orbit, the laser links physically cannot exceed 5,000 kilometers or else they will run into the atmosphere and the Earth. When I look at the specs for a coherent long distance 200 gigabit fiber transceiver, the minimum receiver power falls right into this range. And this is no coincidence. You can see these transceivers have a few modulation options, including lower data rates, and usually more parallelized options with lower spectral efficiency per channel require non-linearly less power, just as in RF. The same webpage has a 400 gigabit transceiver and an erbium-doped fiber amplifier, and it is not hard to find optical amplifiers of 2 watts or higher online. So it is safe to assume that Starlink V2 and V3 use similar coherent optical transceivers paired with their custom optics, pointing and control system, and networking protocol. Beyond that, there is not much to go off for further reverse engineering, so let's move on to space-Earth laser links. The most impressive technology demonstration so far is T-Bird, launched by NASA in 2022. This payload achieved a 200 gigabit data rate at 1 watt output and only a 2 centimeter transmit optic, albeit with a 1 meter ground telescope as the receiver. This ground telescope is part of the Optical Communications Telescope Laboratory near JPL in Southern California. It has an adaptive optics system that can correct over 15 decibels of coupling losses from turbulence, an advanced coherent detector, and beaconing and uplink lasers. The T-Bird payload also had an optical receiver from the ground, and this was operated at just 2 kilobits per second as a pointing beacon and for lost packet retransmission requests. It used 2 wavelengths of dual polarization QPSK with Ethernet framing and operated out to 930 kilometers slant range. The authors of a review of the mission results also proposed some operational systems resembling this demonstration. Both use a larger but still relatively low-gain transmit laser with either a 25 centimeter ground telescope at 200 gigabits per second or a 60 centimeter telescope at 800 gigabits per second. When we look at the results for the losses, you may be surprised that the atmospheric loss is less than a single decibel, and this is because the attenuation is very low. 1550 nanometer light, in particular, is a strong transmission window with very low attenuation. So only the turbulence produces significant atmospheric losses, at least in perfectly clear weather. And the 5.7 decibel coupling loss term here is probably the most unexpected and significant result of this demonstration. The full adaptive optics design performed as expected in terms of power at the receiver, but the coupling efficiency was lower due to significant power fluctuations. We will return to this result in the simulation section of this video. Now let's go through the attenuation terms. First, we have all of the greenhouse gases: water, carbon dioxide, methane, etc. These block most of the infrared spectrum, with a few gaps in shortwave and near infrared. Oxygen and Rayleigh scattering block some visible and near infrared, but most of it can pass through the atmosphere. Aerosols also affect shorter wavelengths, but unless you have fires or thick smog or a dust storm, it is not too strong at 1550 nanometers. The most serious attenuation problem is weather. When I enable clouds or fog, everything is scattered across the entire spectrum. You simply cannot shoot lasers through clouds or fog. The effects of air turbulence are more complicated to quantify than attenuation. In astronomy imaging, where we are dealing with light that passes through the atmosphere near the telescope, we are concerned with the wavefront aberration, which distorts the image of point sources like stars into blurs or scatters instead of a nice airy disk pattern. This is also true in optical communications for a single-mode Gaussian pattern of an incoming laser. This can be described with the point spread function, and the quality of the point spread function is quantified with the Strehl ratio. The Strehl ratio is the ratio of the peak intensity to that of the ideal aberration-free point spread function of the given aperture. If the aperture is partially blocked by the secondary mirror and structural beams, these distortions are not counted against the Strehl ratio. It just accounts for turbulence and optical aberrations like spherical aberration, astigmatism, or chromatic aberration in the case of a lens. Laser telescope designs aim to limit this distortion to launch Gaussian mode beams and couple incoming beams into single mode fiber for coherent detection, so the secondary mirrors are often smaller or placed off axis to retain a clear aperture. Lenses are also a common choice for smaller apertures. For broad spectrum white light, the chromatic aberration can be an issue in lenses, but for narrow linewidth lasers, it can work fine. A Strehl ratio of 0.8 or greater is considered diffraction limited, and if it is lower, it is either limited by aberrations in the telescope optics or it can be turbulence limited. The distorted lower Strehl ratio point spread functions result in more transverse modes. So if you aim a low Strehl ratio point spread function into a single mode fiber, very little of the light will couple into it, and this is why coupling efficiency is strongly correlated with Strehl ratio. You can predict if the telescope will be turbulence limited before adaptive optics through the spatial coherence length, also known as the Fried parameter. This represents the diameter of patches over the aperture where the wavefront is relatively smooth. Formally, it is the diameter where the RMS average phase error is below 1 radian. In imaging, we are not measuring phase. However, since the guide star is a coherent plane wave source, the phase error represents an angular wavefront error. When the aperture diameter exceeds the Fried parameter, without adaptive optics, it will become turbulence limited, where the resolution cannot exceed that of a telescope with the diameter matching the Fried parameter. Here you can see the Strehl ratio and the point spread function at different aperture diameter to Fried parameter ratios, and you can see that the performance drops rapidly when the aperture is greater than the Fried parameter. The chart on top also shows how turbulence is less detrimental for very short exposures, and some techniques take advantage of this to achieve better image quality. The Fried parameter depends on the location, elevation angle, atmospheric conditions, and wavelength, and so to standardize, it is usually reported implicitly for 90 degrees elevation and 500 nanometer light. In good conditions, the Fried parameter will be around 10 to 20 centimeters for visible and around 50 centimeters at 1550 nanometers. Generally, dry, high-altitude locations like mountain summits and the Atacama Desert will have the best Fried parameters, which is why we build telescopes there. Here I show two of the best sites with the less ideal sea level Los Angeles. What I show here is for average nighttime conditions at 90 degrees elevation angle, but depending on time of day and elevation and various other factors, the turbulence can be significantly worse. And if you're not aware, you can use shortwave infrared telescopes and laser links during the day, since the sky mostly scatters shorter wavelength visible blue light. However, you still cannot point your telescope at or near the sun. To correct for turbulence, large telescopes use adaptive optics. These systems work by first aiming the telescope at a guide star. This can be an actual star or an artificial star created with a laser. Large telescopes will use many artificial guide stars at once for tomography of the atmosphere, and different wavelength lasers will produce guide stars at different altitudes with either sodium absorption or Rayleigh scattering. For optical communications, you can use the incoming laser as the guide star. A portion of the image that includes the guide star will be split into different aperture cells and sent to a wavefront sensor, which will record the phase disturbances of the wavefront. These measurements are used to calculate corrections, which are passed on to deformable and/or steerable mirrors that will correct turbulence and vibration disturbances in a closed loop. The corrections will update hundreds of times per second in large modern telescopes, which is much faster than changes in wind. However, in optical communications, the satellite is moving across the sky at a very high angular rate. At 500 kilometers, this equals up to 1 degree or 15 milliradians per second. At 10 kilometers in the atmosphere and 15 milliradians per second angular speed, the beam sweeps out 150 meters per second. So the beam is passing through many different columns of turbulent air, each of which have their own changing winds. Therefore, a much faster adaptive optics update speed is required compared to an ordinary telescope. The optical ground station 1 used in the T-Bird test updates at 5 to 20 kilohertz. Interestingly, Earth imaging satellites do not use real-time adaptive optics, and they do not need to. For these telescopes, instead of a coherent point source from a star being disturbed just before it reaches the aperture in the near field, sunlight is reflected as a distributed source across the ground, disturbed, then it passes undisturbed for a long distance through free space, where it reaches the aperture under close to far field conditions. In other words, for a given pixel on the imaging plane, the light can only arrive at the satellite aperture from a narrow direction range, and the wavefront from a point source cannot be significantly curved, since it cannot be disturbed anywhere near the aperture. There are still turbulence effects, such as rapid translations in the image, but generally the Strel ratio remains very high compared to ground telescopes looking into space. Furthermore, the turbulence is different for every pixel in the scene, so correcting it across the entire scene is impossible. Likewise, the turbulence effects of uplink and downlink optical communications are different. On downlink, the light travels hundreds of kilometers as a collimated Gaussian beam and arrives at the top of the atmosphere as a tight laser spot. At just 10 to 20 kilometers from the receive aperture, the wavefront will start to be distorted, but much of the light will still reach the ground telescope. There, the adaptive optics can correct the disturbed wavefront. On uplink, the collimated beam will start to be distorted as soon as it leaves the transmitter. If there is strong turbulence, it will arrive at the top of the atmosphere as a very broad and shifted point spread function with a distorted wavefront that will diffract light in many different directions. Therefore, very little light will even reach the telescope, and since the light will still arrive as a plane wave, there is nothing that the adaptive optics can correct. However, if the adaptive optics system could apply a pre-distortion to the transmitter, that is, the inverse of the distortion caused by atmospheric turbulence, the light can arrive at the top of the atmosphere as a tight point spread function and then travel to the satellite as a collimated beam. The challenge with uplink adaptive optics, however, is that you cannot ideally correct the wavefront when using the downlink beam as the guide star. In the time it takes light to travel between the satellite and the ground station, 1.6 milliseconds for 500 kilometers, the satellite moves across the sky and the angular position changes along with the column of turbulent air between the satellite and ground station. This change in angle between the uplink and downlink is called the point-ahead angle. At higher altitude orbits, satellites move across the sky slower, but the latency is also higher, so the point-ahead angle at geostationary orbit is still about 20 microradians, which is about half that of the 50 microradians in low Earth orbit. You may be surprised that a point-ahead angle exists at GEO since it is stationary in the sky. However, this is only in the rotating Earth-fixed reference frame. In the inertial frame, geostationary satellites are actually orbiting the Earth at 3,000 meters per second, and lasers move in straight lines in the inertial frame, so you still cannot point straight at the target in both uplink and downlink. This point-ahead angle creates a problem known as anisoplanetism, where beyond a certain angle, using the correction for a guide star becomes invalid due to unaccounted for turbulence. That angle is called the anisoplanatic angle, and it also varies with atmospheric conditions, just like the Freed parameter. At moderate elevation angles, the anisoplanatic angle will often be less than or equal to the point-ahead angle. So the corrections valid for the downlink signal, which is treated as the guide star, cannot be used to ideally predistort the wavefront of the uplink signal because you need to point to where the satellite will be in a different angular position, which is a different column of turbulent air. We have a few options for dealing with this. First is to simply not use adaptive optics, and this can be a valid choice for very small, diffraction-limited apertures well below the Fried length. Next, you can choose to still use only the downlink signal as the guide star as an approximation, and this can be tip-tilt mirror corrected only. This is only low-order corrections, which will mainly just keep the focal point centered to fix jitter and beam wander. These corrections can work well even when the point-ahead angle is somewhat large. Using both tip-tilt and deformable mirrors can correct higher-order aberrations to the wavefront that spread out the point spread function. By high order, this means involving more degrees of freedom and higher spatial frequencies. So the tip-tilt mirror and broad deformable mirror shape changes are low order, and more complicated changes to astigmatism, for example, would be high order. The lowest order 0-0 mode you see here is called piston, which is a longitudinal shift of the whole wavefront, which does not distort the PSF, and therefore does not need to be corrected with adaptive optics. These combined corrections can work in good conditions with the downlink laser as the guide star, but higher order corrections work better with an artificial laser guide star in the actual direction of the uplink. The laser guide star can be less reliable for lower order tip-tilt corrections, so this mode often keeps the downlink laser input for the lower order corrections since the lower turbulent layers of the atmosphere are still shared between the two beams. I'm using these definitions from this paper that quantifies the turbulence effects on uplink. They used an atmospheric turbulence simulation and did a Monte Carlo simulation with lots of different configurations to estimate the performance across all of these different adaptive optics modes. It had some interesting results that we'll go over briefly now. This plot shows the intensity at the receiver at 3 different sizes for the transmitter beam radius with all of the different adaptive optics methods. You can see that a 2 centimeter radius beam will work decently well without adaptive optics since it is diffraction limited. The 10 centimeter radius beam becomes very unreliable without tip-tilt correction. Then at 20 centimeters, both the lower and higher order adaptive optics corrections are absolutely needed. And also keep in mind as we go through these that this is for a specific atmospheric environment at some specific coherence length or free parameter. Surprisingly, the downlink guide star is nearly optimal, and the artificial laser guide star only provides a small improvement even for this large aperture laser. However, average power received is not the only important metric. This plot on the right shows the normalized intensity variance, also known as scintillation index. This is the fading and surging in amplitude caused by turbulence. The green and red lines, representing the downlink guide star or point-ahead guide star modes, produce nearly the same intensity, but somewhat different variance in intensity. For reference, in these specific conditions, a Starlink-sized ground terminal would be here at a scintillation index of just under around 0.5 without adaptive optics. That equals a normalized standard deviation of 0.7, so that is unacceptable at any intensity or modulation type. However, with a laser guide star, the variance would drop to just 1% of the average, and that is more acceptable, although still somewhat noisy. There is also an interesting relationship here where the uncorrected performance gets worse as beam size increases without adaptive optics, but with adaptive optics it improves and then gets worse again. And this little sweet spot for adaptive optics falls into the 25 to 60 centimeter diameter proposed by the T-Bird scientists. Although that proposal was only optimizing for downlink, not uplink, as is being simulated here. In this next chart, they use the calculated variance with an assumption of direct detection on off-keying to calculate probability of fade and bit error rate. The top chart has the fade condition on the x-axis. So for example, if 5 decibels weaker than average signal is the threshold for a fade, then it would have the given probability at each beam size and adaptive optics setting. The bottom chart is a standard signal-to-noise ratio versus uncorrected bit error rate. You can imagine for the lines that significantly slope down that if you added forward error correction, coding gain, and had error detection and data retransmission, then they would be very reliable communication systems. And the outlier shallow lines would need relatively impractical signal-to-noise ratios to function well. The authors of this paper have a lightweight open source version of this simulator for both uplink and downlink adaptive optics called FAST, and I use these Python scripts in the background as the adaptive optics and turbulence model for my optical link budget simulator. Here we are on our optical link budget simulator, and I'm going to spend a lot of time going through this and going through various scenarios because this should give you a much better understanding of turbulence and optics than just looking at those graphs. And we're also going to go through many more scenarios than what they showed in that paper. So what makes this program possible is to run the fast simulation in the background. And if you are using it on my GitHub page, there is a script that will launch this Python instance in the background that will run all of this. And then there's also a browser port that I made that's kind of the backup, and it just runs a bit slower, but I tested it and it has statistically identical outputs. So you can use that as well. First, what's going to happen, you're going to input all of this stuff. These are all of the inputs that are needed for the fast. And so that's all of your lasers and optics configurations, and then all of your adaptive optics settings. And then this will export a configuration. This will have all of these options, and it's just going to run that in that adaptive optics and turbulence simulator. That will output the scintillation index and the average power and most of the other things that we will use to derive all of our metrics. The F in FAST stands for Fourier domain. And so one of the very important outputs is this phase spectral density. This is analytically calculating the wavefront disturbances based on different spatial frequencies. And then depending on your adaptive optics settings, it will correct some of this and there will still be some residual. So in full adaptive optics, it will correct both the low spatial frequencies and the high spatial frequencies. And just to show you what happens when we change our adaptive optics settings, and this is for downlink as of right now. If we move to tip tilt, that will correct only these lower spatial frequencies. And then if we move to, wrong setting, if we move to no adaptive optics, it will correct none of it. I've also added on a lot of stuff into the simulator to make this more intuitive and provide some visuals. So some things I've added on are these point spread function calculations. I also have this analytical generation of symbols based on several different modulation types. And then I also have a bit error rate model for each of those different types of modulations. Before we get into that, I first want to show you a validation of the model so that you at least know that it is somewhat accurate. And so the first thing I want to try for this is, and I've already done this ahead of time, is calculating the freed parameters. And the first thing we're going to do is we're going to use the T-bird scenario because that's well documented in lots of papers of their results. And the first thing I'm going to do is calculate the freed parameter. So in this case, we're going to move to 500 nanometer light, and this is a 90-degree elevation angle. And when we run this simulation, this is for a median night scenario. So in the T-bird results paper, they usually talked about their nighttime conditions in the range of 6 to 11 centimeters. And so here we have median night is giving us 10 centimeters. If we go to stable night, that's our most ideal scenario, we get 13 centimeters. So that's somewhat valid so far. And they also mentioned 2 to 4 centimeters is somewhat turbulent conditions during the day. So I have these different models for different times of day and different conditions at all these different locations. This is Table Mountain, where the OGS-1 ground station they used with T-bird is. And so when we run this, we get 2.72 centimeters. So based on these results, my atmospheric modeling is somewhat validated. One of the things I forgot to mention about the simulation is that one of these outputs is the Rydtop variance. This is going to be related to the scintillation with no adaptive optics turned on. And this program is mainly tested and validated for weak turbulence, the FAST program. And so just keep that in mind. Take the very high turbulence scenarios with a small grain of salt. Okay, next we're going to try to validate our power received model. So in the T-bird, one of the T-bird results papers, they gave a scenario of a link budget at 25 degrees. Okay, so here we're back to our 25-degree elevation angle. This is for median night. And when I first created this empirical model, I used 0 additional coupling loss here. So this is just considering the coupling loss based on the atmospheric effects. And I got minus 31 decibels, or sorry, decibel milliwatts. And that's compared to the minus 35 milliwatts that they reported in their paper. So it was a little off. And then by the way, depending on the atmospheric conditions, the power received is still around the same because of the adaptive optics. And I'll show that in just a second. So for the T-bird model specifically, within their papers, they talked about an additional coupling loss that was more than what they would expect from the atmosphere with adaptive optics. And so to correct for this, we're just adding an additional 4 decibels of coupling loss. And this gives us the around minus 35 decibels for this scenario. And in those papers, they don't exactly explain what the cause of it was, but they did say that it did cause very deep fading And so it's possible that has something to do with the jitter or the adaptive optics system or some sort of noise. But anyway, when I do the scenarios later for TeraWave and whatnot, I'm going to not use this additional coupling loss tentatively, but we'll just keep that in mind that that also could affect smaller systems and even systems that don't have adaptive optics. However, another thing to keep in mind is that the single mode fiber coupling loss only affects coherent detection, because when you're using direct detection, you don't need to couple it into a single mode fiber first, because you're not going to be doing optical interferometry with a local oscillator. And so you can just focus that directly on to the focal plane sensors, the photodiodes. And so specifically in the T-Bird scenario, we can expect somewhat higher power in the same geometry using direct detection. There's also some academic research into using multimode fiber for coherent detection. However, my understanding is that that doesn't always work perfectly because the laser is usually single mode, the local oscillator laser. So anyway, we're just going to ignore that point for now. One final bit of validation I want to do is my bit error rate calculation, because in those papers, they stated that when they have minus 41 dBm for their power received, that was their threshold for their 100 gigabit data rate. So to achieve this, we're just going to lower the elevation down quite a bit. And 10 degrees was actually the minimum of what they used on their charts. Yeah, so here we have around minus 41 dBm. And our calculated bit error rate is 0.06. And just looking at our constellation, it looks fairly noisy, and the bit error rate is kind of high. However, if you have a very good forward error correction, this is still somewhat reasonable to achieve that 100 gigabits. Oh, and I also forgot to lower the baud rate down to 50. When we run this again, we get it even lower, 0.017. And so that's pretty reasonable to correct with forward error correction. Okay, now that we've validated our program, at least for the specific T-Bird scenario, I'm going to take you through a few examples to give you a good understanding of this turbulence. So here is the basic T-Bird setup. This is the point spread function of the transmitter as it goes through the atmosphere. The transmitter has a very wide divergence angle, and the aperture is something around the size of 2 centimeters, 1 centimeter. And because that's much lower than the coherence length, it does not significantly distort on the macro level. However, at the small level, say the size of the aperture, that wavefront will still distort significantly without adaptive optics. And so here, if we turn off the full adaptive optics setting that's currently correcting all of these frequencies, and we move to just tip tilt on this large 1 meter mirror, you can see now we're just correcting these lower frequencies and not as successfully. Now the macro PSF is still going to look the same, it's still the same downlink, but the sensor wavefront is going to be significantly distorted, and the tip tilt sensor cannot fully correct all of those aberrations. So let's compare this to the full corrections in the full adaptive optics. And here you can see it requires a much more complicated correction from the deformable mirror to actually properly correct this. Now, if we go to no adaptive optics, this is just no corrections. And likewise, it's going to be very distorted. And even though the power received is somewhat decent, the scintillation index is so high that your bit error rate is going to be unacceptable. And so you need to consider both of these when you're looking at the link budget. So that's been the T-Bird scenario on downlink, but now I want to show you what would have happened if they tried to use this exact same setup on uplink. So when we move to uplink, and we look at our macro PSF, this is the distortion going through the atmosphere. And if you recall, this is using the full adaptive optics in the direction of the downlink, not in the exact direction of the uplink. And if you look at the divergence angle, that's 2 microradians. The point ahead angle is 50 microradians. So they would not be able to use the full diameter aperture to do uplink and downlink at the same time, because the downlink beam would be way the heck over here, and the uplink beam is right here. So if they actually wanted to do that, they would need 2 telescopes on the ground and potentially 2 telescopes in space. The solution that the NASA scientists came up with is to just use a very high divergence beam on the ground as the transmit. And in this case, it's around 600 or 500 microradians. And then so even with the 50 microradian point ahead angle, it's going to include both the uplink and downlink directions in this giant point spread function in space. And you can see this is 1 kilometer across, and the satellite is only moving a tiny fraction of that during this trip. The Strel ratio, the coupling efficiency, those are all going to be relatively good. And actually, we're going to use direct detection with this anyway. And so let's just throw that in already, direct. Okay, and so the problem though is that both the transmit and receive have very low gain, very high divergence, and so the power received is going to be very low, and so you can't do a full 200 gigabit with these tiny aperture transmitter and receiver terminals. So what they did, or what you do, is you just lower the symbol rate, and that will fix your shot noise problem. In this case, we have 0.25 photons per bit. And so it was binary ppm, but that's equivalent to on-off keying with Manchester coding. And they only used 2 kilobits. So something like this, we'll let that run. And now, even though we have minus 55 dBm, it's still a very low power received. We have 1 million photons per bit. And so that's going to get rid of all the shot noise, and we can still have an effective direct detection setup here. Now, because these apertures are so small, you're going to see that it doesn't really matter that much whether we're using adaptive optics or not. So here we're using adaptive optics. I'll go all the way to laser guide star plus tip tilt. That's full adaptive optics with laser guide star in the uplink direction. And so you can see, even with the ideal adaptive optics setup, it really doesn't matter that much because these are so far below the coherence length, the free parameter. So anyway, that's how the T-Bird uplink worked. And now I want to go through the other options that they talked about in their paper. Okay, so after the T-Bird people shared their results, they gave some options for the operational concepts for an actual system. And the idea was to slightly increase the terminal on the spacecraft, but still relatively small. We're going to call it like 5 centimeters, something like that. And then they want to use either a 0.6 or 0.25 meter mirror on the ground. And so 0.6 is pretty much the same size as the existing one. And that would be really expensive somewhat, but you can see we get a very good signal to noise ratio. And so their idea was you could go up to 400 gigabits. So I guess that would be 16 QAM. That would either be 16 QAM, you could even pull that off, or you could do 4 QAM with QPSK. You could do QPSK with 2 polarizations. That would kind of give you the same result. You can see it's very strong. There's just a little bit of scintillation, barely no shot noise like this. So that would work. Now the issue is that would probably not work with tip tilt. Let's try it. When you have tip tilt on such a large aperture, 0.6 meters, that is going to give you a pretty messy wavefront, and it's going to cause a scintillation index of 1, okay? So the other option was 0.25, and they even mentioned, and that was the goal, was to use full adaptive optics with that system. Let me look here. Okay, now we're going to switch to full AO with 0.25 ground aperture, and that works very well. Let's look at these. Yeah, so you could even potentially do 400 gigabit with that, but they said that would be 200 gigabit. I might be overestimating how large they wanted this satellite aperture to be. It might still be closer to 2 or 3 centimeters or something like that, but it was 90 decibels of gain. So I'll let you guys do the math on that one. But now if we go to tip tilt, this should still somewhat work. Okay. And we still do get a fairly good bit error rate here. So this matches what they were saying in the paper as well. That's just one more little piece of validation. However, if you go to no adaptive optics, there you would potentially run into a problem. Okay. Let's say if the elevation angle is a bit lower. Oh, and also I haven't showed yet if you showed some other location. So Table Mountain is around 3,000 feet, 1,000 meters. And so if you actually just used some random site like Los Angeles, or actually we have this Florida site is just like a baseline sea level location. And if we run this, now we're starting to get into some problems. And let's run it in Los Angeles just to show you the different options. Yeah, so then now if you try to use tip tilt with this is with no adaptive optics. If you tried to use no adaptive optics on 0.25 in Los Angeles, that would probably not work. Okay, even with the larger satellite that thing. And you can see the PSF is still not too distorted on the macro level. On the sensor level it is. So because of this problem, my intuition would be to use a larger aperture in space and then a smaller aperture on the ground. So let's see what it looks like with that. So okay, we're going to change back to Table Mountain since the Los Angeles turbulence is pretty high. So 6 centimeters. Let's use a 6 centimeter ground terminal, and then in space we'll use a 10 centimeter. And you can see this works fairly well even during daytime. And let's try this in Los Angeles just to check. Okay, that's a bit questionable bit error rate, but potentially you could make a system. Oh no, the scintillation index is 4. Okay, that's a bit questionable. You don't really want to try to use adaptive optics in a bad turbulence location like Los Angeles. So we'll just ignore that for now. So this kind of setup will more or less work. And then even you can just copy the Starlink size terminals with no adaptive optics. And yeah, and so these would probably work relatively well. This is even with the additional coupling loss. If we turn this off, and then if we throw in tip tilt on downlink, then this can give you a very reliable kind of system. So if you just have good locations, then this seems possible. And here's the exact same scenario on uplink. It's still pretty much working. This would be a little bit questionable. You might want to go a little bit smaller on the ground terminal so that you don't have a really high scintillation index like this because of the turbulence. And then potentially you could do tip tilt on the uplink compensation as well. That'll help. Okay, so tip tilt would be sort of effective at this. Now, the problem is just like in the T-bird scenario I talked about. Our divergence angle is 15 microradians, and our point ahead angle is 50 microradians. So you're pointing over here, and the two beams are in different spots. And so if you want to just try to use Starlink terminals, in theory, assuming that would work, then you either need to do only downlink or only uplink. And if you want to do both at the same time, then you would need 2 sets of terminals. So those are the basic trade-offs there. Speaking of laser terminals, let's go through again and take a look at the Starlink scenario. So here is sort of a basic 1200 kilometer laser link. This is something you might expect. We have minus 23 decibels here. And if you look at our Constellation plot, it's very clean. And so they could use this for 200 gigabit terminals or 400 gigabit terminals. This would be 400 gigabit. And the link seems like it would be perfectly fine. And this is very simple. You can just use the Friese equation because the turbulence-induced straw ratio is 0 because there's no atmosphere. Now, like I said earlier, just to show you, the absolute maximum distance can only be so far until it smashes into the Earth. So it's going to be something like 5,000. Okay, and this is even excessive. If you look at the Starlink constellation, they're spaced very close together. So the only reason they would want to do this is for some long-distance routing where they wanted to use fewer terminals and just use the bandwidth a bit more efficiently. But this is still pretty impractical, and let's see what the power received is. But even at this distance, we get a somewhat manageable signal-to-noise ratio here. So they could even potentially be using smaller apertures. I may be overestimating what they're using here, but the link budgets are fairly clean for low Earth orbit to low Earth orbit. Okay, and just to show off a few more things in this app I made, here we have an airplane scenario, and you can see optical communications can work for airplanes, although it's kind of like overkill and not necessary. You can just use RF or just use satellite communications with the plane. You can just have the plane shoot RF into space. And that's also not practical because of weather, or even humidity. So just like in, we've already talked about this, but if you had any clouds at all, then your link budget is going to be destroyed no matter what. We have minus 1,000 decibels getting through the clouds here. And so it's just impossible. And I didn't show that, but the same is true for pointing down from space to Earth, and 70% of the Earth has clouds. Now you can also use this for looking at laser weapons or using this for LiDAR type scenarios. So here this is the iron beam setup. It's 0.5, and we're going to change this power to 100,000. And you can see this is with it collimated. 100,000. This is with the beam collimated. So if we change to focused, you're going to see it's going to get much smaller, but it'll still be fairly distorted. Yeah, so this is a 1 meter circle. Okay, but the thing is still very distorted. And this is the limitation of laser weapons. is that in the atmosphere, they have to face turbulence, and the Strel ratio drops to like 0.01 beyond a certain distance. And then if you add in aerosols or fog and anything like that, they just become somewhat unreliable. And so this holds up relatively well with my laser weapon video. However, in that video, we did talk about how this can still kind of work. So you're focusing 100,000 watts. It doesn't need to be focused into a perfect spot on something like a drone, because you have, in this case, 88 megawatts per square meter. And so something like that can still start a fire, even if it's not perfectly focused. Now, if you have to melt through aluminum and steel, like on a satellite or on a missile, then you need to have, ideally, you can try to have some form of adaptive optics. So if we do uplink compensation, apparently it's not possible to use the reflection of your laser for adaptive optics. But yeah, beyond a certain turbulence, it just falls apart. So let's go to a stable night and see how it works now. Yeah, so if you have a stable night, if the turbulence conditions are good, now you can have some crazy kind of air defense laser system. If you put it at Table Mountain or Mauna Kea, for example, then you can actually properly focus your laser onto your target. Okay, here's another scenario we had from my laser weapons video. This is a 2 megawatt laser, and this is a somewhat bad M squared. So watch what happens when I change the M squared here. It'll go to a more focused laser point. And we were talking about how this is kind of impractical. So anyway, the laser weapon stuff still mostly holds up from that old video. Okay, the last thing I want to show off is my deep space presets. So here we have the moon. Let's run this. This is with a ppm setup. So this is using 64 ppm. Here you can see this plot isn't showing which slot it thinks the symbol is in. This is how much power is received on average per slot. So in this case, it's like a very high signal to noise ratio. And this is based on they use the Hale telescope. It's 5.1 meters. I think we already talked about this. And a 22 centimeter aperture receiver. And so in this case, you can have fairly high data rates out to the moon if you use optical. And this is kind of becoming the replacement for the deep space network, which previously had to use these giant X-band antennas. Okay, now as we go out from the moon to Mars, the signal to noise ratio gets a little lower, and your absolute power received drops down to minus 84 dBm. So then it becomes much more challenging. And in this case, we have the baud rate set way too high. So we're going to lower this down. This is still maybe around megabit per second range. And now we have a functional system like this. Now, an interesting thing is when you try to use coherent. Okay, so here's trying to use coherent at a very low baud rate. And I've turned all of the electrical noise all the way down. And here we still have 82 photons per bit. But because our coherence times and our symbol times are starting to become long, we get this weird phase rotation error that I was showing earlier. Now let's try Pluto. Okay, here we are at Pluto. We have way too much shot noise based on the previous settings. So we need to turn down our, okay, so here I turned down all our noise settings, since this would be like a single photon detector. And you can see we're at minus 108 dBm. That's like barely any power at all. However, if you have a very sensitive direct detector, you can still have a signal if you're willing to use a lot of sampling bandwidth. And it's not even that much in this case. But this is pretty important for space missions like New Horizons. A big deal was that they only had so much time to transmit the high resolution photos of Pluto, and that is a limitation for these missions. And it's also a limitation to use the deep space network for everything. This could be an important thing in the future to use lasers for long distances. Okay, one more thing I wanted to just talk about is this is a T-bird uplink type scenario, except with relatively bad conditions. And I just want to show that the signal will go through the atmosphere and it'll get distorted. It will look like this at the top of the atmosphere, except not as spread out. And then as it spreads out, that curved wavefront at the micro level will sort of flatten as it moves into the far field. And so on the sensor, you can still get this good point spread function, but with a terrible scintillation index, because in real time, this is going to be jittering all around. This is similar to what happens in imaging satellites. Because the distortion is so far away from the aperture, the point spread function is still acceptable. Also, no point sources on the ground or no distributed diffuse reflections on the ground will be doing something like this. Every reflective point on the ground will just be shooting a plane wave into space. It would look even larger than this. And so this is why the Strel ratio is essentially always maintained on satellites. So I hope you guys liked this demo. I encourage you to go on my GitHub page and try this out, in addition to my RF demos and all the other files. And I think this will really help you get a good intuition for this kind of thing. But for now, it's time to move on to this video's main topic of discussion, which is Blue Origin's TeraWave constellation. In January, they announced the constellation of 5,280 low Earth orbit RF satellites with speeds up to 144 gigabits per second for both uplink and downlink. These satellites will have optical intersatellite links and also connect to 128 optical-only satellites in medium Earth orbit. They would also connect through the atmosphere to optical ground stations at 6 terabits throughput. The intended customers are enterprise data centers and government, essentially aiming to compete with long-distance fiber. Based on the FCC filings, the low Earth orbit satellites will be at around 530 kilometers altitude, and most of the medium Earth orbit satellites will be at 8,000 kilometers. The RF user links are in V-band, 4.5 GHz for downlink and 4 GHz for uplink, and the backhaul links are E-band, 5 GHz for both uplink and downlink. And everything is dual polarization. This design is similar to the Starlink V3 V-band phased array antennas, although the gain is about 12 decibels below Starlink's large 55 decibel V-band antenna. The effective isotropic radiated power is 15 decibels lower, and the altitude is over 150 kilometers higher than Starlink V3. So if you add all of that up, the link budget is around 18 decibels worse, assuming the same receive antenna gain. However, the system is still functional. As you see in my RF link budget sim here, in ideal conditions, you could get 2 bits per hertz, low code rate 16 QAM. Then, depending on your elevation angle, you would need to use lower code rate QPSK. So typically, you get around 10 to 15 gigabits per dual polarization link. The listed minimum elevation is 25 degrees, and there, even a light drizzle of rain would knock out the link without decreasing bandwidth and further decreasing the data rate. However, with 5,000 satellites in the constellation, you could connect to several satellites at decent elevation angles at the same time. And at 90 degrees elevation, it can still function at full bandwidth out to moderate to heavy rain. At 50 degrees elevation, it looks slightly less dense than Starlink, so this would be believable to get the advertised data rate of 144 gigabits per second. This assumes a multi-beam user terminal phased array that is the same gain as the satellite, which would be about 40 centimeters in diameter. Also, this simulation is not including phased array steering losses, so if connected to 10 satellites at once, it could not point at all of them at the same time physically to achieve max gain, and so the average gain and link budget would be slightly worse. When we compare to Starlink V3 V-band, we start with a much better link budget. At good elevation angles, we can use high code rate 64 QAM and still have higher data rates with single polarization out to 10 degrees elevation. It can handle somewhat heavy rain at ideal elevation angle, but in a severe storm, it would still get knocked out at full bandwidth and need to lower the data rate, or get knocked out completely. So the TeraWave weather reliability would be somewhat worse, and the swath size would be much larger than Starlink, so you cannot serve as many users in the same area with the same satellite. And the power per beam is still higher than Starlink. So it is definitely inferior to Starlink V-band, but it is still a valid design for what it is. The FCC explicitly does not regulate laser links, so there is no published technical information about the TeraWave optical links other than the 6 terabit data rate and some job postings which imply some already obvious design choices like wavelength division multiplexing and coherent detection. So to analyze the system, we are going to use our adaptive optics laser simulator, but first let's just look over the constellation plan and talk some business. The low Earth orbit satellites are already connected between each other with laser links and to users and backhaul ground stations with RF links, so for ordinary regional internet, there is no need to use the medium Earth orbit shells. Furthermore, 6 terabit Earth-to-space optical links are useless for internet for individual users. Everywhere on Earth has occasional cloudy days and morning fog, and storms can cover entire regions for weeks. In fact, on average, 67% of the Earth is covered in clouds, so clear weather is actually the outlier. Therefore, data centers would never choose this option over regional fiber, even if it were somehow cheaper and higher capacity, which it is not. The only potential customers would need to be either extremely distributed or based in space where there are no clouds. One very plausible use case is replacing undersea fiber for 180-degree cross-planet internet connections. For example, to connect a user in New York to Singapore, the message needs to be routed through several undersea cables, many different countries and jurisdictions, and along the way, it likely uses up bandwidth and amplifier and digital processing power on dozens or hundreds of different transceivers and links. Even if a low Earth orbit constellation like Starlink is used, that would still require dozens of connections with more limited bandwidth. A more efficient strategy could be for whichever US data center has clear weather to optically connect to medium Earth orbit, make one hop from MEO to MEO, then connect to a data center in Southeast Asia with clear weather. Presumably, these would be placed in desert and mountainous areas of each region as well, so that they could mostly avoid clouds. If we assume each satellite has 5 transceivers, then 6 times 5 times 128 MEO satellites would be 3.8 petabits, which is more than all Atlantic undersea cables combined. So assuming these are somewhat light satellites, they could get very high capacity with relatively few launches. If all the links connected to the exact opposite side of the planet, then undersea fiber could be used only for regional connections, and that would plausibly improve efficiency. Despite these being in higher orbit, the latency is probably slightly better than fiber, since there are much fewer processing steps, and the light travels faster in space, which cancels out the less optimal geometry. Amazon Web Services would be a good customer to start with. However, they are building their own low Earth orbit constellation. Interestingly, Amazon satellites use the exact same V-band allocation used to connect customer terminals, and the antenna beams have nearly the same gain. These Amazon LEO satellites also have Ku and Ka band user links, and they just announced direct-to-cell satellites to use their spectrum from their Globalstar acquisition. If you weren't aware, Jeff Bezos is the founder and largest shareholder of both Amazon and Blue Origin, so the plan to compete with himself with basically the exact same payloads on 2 different constellations is a bit confusing, but it's possible he is trying to merge these constellations or to merge these companies together or some other sort of master plan. The internet infrastructure play seems like an okay business model, but the real killer use case I see is satellite backhaul, especially for remote sensing satellites. Let's first take, for example, the Worldview satellite with a 1-meter mirror, which will provide a diffraction-limited resolution of 33 centimeters at 500 kilometers slant range. Theoretically, you would sample at the Nyquist, so half of that resolution at 16.75 centimeters to get the full diffraction-limited resolution, but apparently this is not always done in practice because there are other resolution limitations. So if you want to use that assumption, multiply all of these values in this section by 4. A typical field of view is 1 degree, producing a footprint of around 10 kilometers across. This will contain around 30,000 33 centimeter pixels on one axis. If we squared that to instantaneously image at full resolution across the full footprint, that comes out to 891 megapixels, which would be as many pixels as 100 4K focal plane arrays, or 20 of the iPhone's 48 megapixel focal plane arrays. So this sensor size has not been used in any satellite I am aware of, but it is entirely possible. For example, the Planet Labs SkySat constellation uses a total of only 16.5 megapixels across 3 sensors, and therefore they cannot image the full 6-kilometer footprint at the same time. Now, if you naively point your telescope down and start sampling at 30 frames per second, you will get a blurry mess since you are moving over the Earth at 7,000 meters per second, equating to 22,000 pixels per second. So you have the option of either counter-rotating your footprint at 10 kilometers per second in a framing mode to keep the same field of view on your imaging focal plane, or you can sample at the 22,000 frames per second as your footprint sweeps across the ground in a push broom mode. Framing modes will focus onto a square focal plane array, while push broom modes will use specialized time delay integration sensors that instantaneously sample only in the cross-track direction at a very high frame rate and extend a short distance in the long-track direction to integrate more of the light focused by the telescope. Imaging spectrometers for hyperspectral imaging add a wavelength dimension. These can be rotated to slow the scroll rate of the footprint across the ground to improve the signal-to-noise ratio of the spectroscopy, and this will also decrease the data rate down to around the same as an imaging push broom. So if we calculate data rates for these scenarios, the actual satellites collect at rates of several gigabits per second for the final product before lossless compression, which likely cuts these data rates in half. These satellites use X-band downlinks of around 1 gigabit for only the few minutes that they are passing overhead ground stations, so they cannot collect all the time, and they have to store only the higher priority imagery to downlink later on. This can add hours of latency from when the imagery is collected to when it can be viewed. You especially don't want latency if you are using the imagery for military purposes, and if you have a medium Earth orbit laser relay, you can just look at a live streamed video from space of whatever the satellite is viewing. And if you have a constellation of at least 100 satellites with laser backhaul, in particular 100 VideoSAR satellites that could see through clouds, then you could get 24/7 video of anywhere on Earth in all weather without having to fly a drone over the target location. You could also put space data centers out at 8,000 kilometers so you could have good solar access and process all the data with AI to only send back the important imagery and information down to Earth. So this laser backhaul would really complete the hypothetical Skynet global surveillance network of the future. The required data rates for remote sensing could grow even higher in the future. For telescopes, with improved optics, you can achieve good quality above 2 degrees field of view. So let's say we go up to 2 meters in aperture size with 16.5 centimeter resolution, and we double the field of view to 2 degrees and 20 kilometers or 400 kilometers squared, and that will increase our number of pixels and our data rate by a factor of 16. So that is just to show that we could collect arbitrarily large amounts of data if data transmission and digital processing were not bottlenecks. And the same is true for synthetic aperture radar. The finished imagery is also around a gigabit per second for relatively low resolution collection on modern commercial satellites. But if you want to process the raw data on Earth or on another satellite, and if you are doing multi-channel with phased arrays at better resolutions and multiple or larger range swaths, then it can also jump up to many terabits per second. So for TeraWave, the medium Earth orbit architecture makes a lot of sense for this use case, since you can link satellites anywhere in low Earth orbit to the United States in just a few hops. Another option is to just use optical instead of higher frequency RF for the backhaul of constellations like Starlink and Amazon Leo. You could link to just a few special satellites with extra cross-plane laser links, and they could pull in and push out data across a large region by connecting through the satellite laser mesh. Especially with the 6 laser links of version 3 Starlink, this would probably work pretty well, even if the ground laser is outside the region it provides backhaul for. In this case, it would make more sense to just do direct to the low Earth orbit satellites instead of going up to medium Earth orbit, so TeraWave MEO satellites would probably not be a great choice for this. Now, before I saw the Starlink version 4 D-band proposal, I thought this would be the killer use case, but now I am not quite sure. Even the version 3 RF backhaul is only 1.2 terabits combined, so several 6 terabit optical links on every satellite would definitely allow them to max out the full potential. And these would need wavelength division multiplexing of probably 15 wavelengths at 200 gigabits per direction. So those would probably cost more than a pair of 6 terabit undersea cable transceivers, which apparently cost around $1 million. The D-band antennas should only be around 2 terabits per link, and they seem like brand new technology that may also cost over $1 million. But it's hard to say, so you guys can let me know which one you think would be cheaper and better in the comments. Also, SpaceX does not have to disclose their optical links in the FCC filings, so it is possible that they are going to use optical backhaul as well, so we'll just have to wait and see. The weather problem of optical could be such a concern that they just don't want to use it, even if it is cheaper and better most of the time. Okay, now we're going to go through and simulate and try to reverse engineer some of these links. So first of all, we have these optical links from 500 kilometer low Earth orbit out to 8,000. And here I've just had the preset here as just Starlink size, 10 centimeters and 1 watt. And you can see here, obviously there's no turbulence, so that's all fine. The power is a bit low at minus 38 decibels. So they could potentially just use much lower data rates. They could do direct detection. They could go down to maybe just a few hundred gigabits, right? Because the RF links are only 144 gigabits per user, spaced out between multiple satellites. So you could also assume the satellites might only have a few hundred gigabits of capacity each for user downlink and user uplink. So you could get a relatively decent direct detection scheme like this. This would still be 50 gigabit per link, and then you can use cheaper transceivers for those specific links potentially. Alternatively, you could stick with the coherent 200 gigabit, 400 gigabit links and just use a larger aperture on the satellite and MEO, since it's going to be having a higher capacity on there, and that will get you to the in the ballpark of the commercial transceiver and Starlink terminal range, minus 33 dBm. Okay, that should give you a fairly good bit error rate. Now, the link out to 24,000 is a bit questionable in my opinion. I'm still not sure what exactly this is going to be used for. Maybe this will just be for the 8,000 kilometer links to more efficiently transmit data to the opposite side of the Earth. But in this case, you would need to, so you're increasing the range by 3 times. And so you square that for your free space path loss. So that's times 9. And so you either need to use significantly larger apertures. So let's say we could do 20 centimeter, 20 centimeter instead, or you'd either do this or you'd use more power to get to a decent power level here. You could also lower your bit rate. I'm not sure why would you want to do that, but those are the options. And then as we've talked about, this would be per lane, right? So this would be per wavelength. You could use 1 watt per wavelength. You could use dozens of different wavelengths like in an undersea cable. It would be exactly like in an undersea cable. And you could just arbitrarily make as many parallel lanes as you want to increase your data rate. Although it does seem really expensive to have these 24,000 satellites. So I think these could be more of a strategic kind of intended for militaries or for the US military, obviously, or for maybe just some special use cases. I'm not really sure. However, most of these optical satellites are going to be the 8,000 kilometer ones. And here I have a basic scenario to a ground station. And I'm using Table Mountain in the afternoon. This is sort of like a more strategically placed infrastructure site. So you put it on somewhere with high elevation and that has relatively low cloud coverage. So, I mean, the Table Mountain would actually be a good location. And the sizes of the terminals are interesting because you would probably not want to use full adaptive optics. It's pretty expensive. They're usually like a custom thing. It's sort of questionable to mass produce those. So let's just set it to tip tilt for now on both uplink and downlink. And then we're going to start with the Starlink size terminals first. And here we get around -40. So like they said in the T-Bird thing, and this is at a relatively shallow elevation angle, 60 degrees. This could be sort of like the average for connecting out to 8,000. But this is going to be pretty low power, and this is also not including that extra 4 decibels of noise there. So when you're going through the atmosphere, number 1, you might want to switch to direct detection. Number 2, you would probably want to increase the size of the satellite aperture and not the ground aperture. So let's just look at that on both downlink and uplink. If we go 0.2 on the satellite aperture, that gets us to -35. That's pretty reasonable. You could just use a good forward error correction. And if we look at how much it spreads out on the Earth, that's not too bad. Now, if we switch to Los Angeles and then run that again, then you're going to have a much more spread out beam. It's probably going to require some more serious adaptive optics on the ground. And so that's why I'm questionable about just using these for any location. And then obviously you have cloud coverage. So my take is that it's just going to be for certain sites, and it's for use cases that they can accept some of the links not working at any given point in time. But anyway, here's Table Mountain with tip tilt. This is on uplink, or that was on downlink, and now we'll look at uplink. And these both are looking relatively good. Let's try it with no adaptive optics. So even with no adaptive optics, if you choose good locations like this, you can make a link work out to 8,000 kilometers. The scintillation index is 0.1, so that's still kind of high. But if you make, especially if you made a custom standard, you worked everything out with the retransmission of packets and all that kind of thing, then you can make a functional system like this. Let's check out direct detection as well, because that's assuming we're not having any extra coupling losses. So direct detection, here we go. We have around the same bit error rate, but around half of the data rate. And potentially, actually, you would want to go back to coherent, and potentially you would want to try to do higher order so that you could have more bandwidth efficiency, more spectral efficiency. Although this will give you sort of questionable conditions. Let's try with better elevation. Yeah, even with good elevation and stuff, this would be questionable without adaptive optics. And if we try this with tip tilt, even with tip tilt, this would be pushing it. So unlike in undersea cables, you probably wouldn't want to go higher order QAM. You'd probably want to stick with QPSK. The scenario is the same for the 24,000. I'm not sure why would you want to have a user terminal all the way out here, because again, you have to somehow improve your link budget by 9 decibels. And at that point, you might as well just go to geostationary orbit. So if you had a location at the equator, then you could just always point it
I mean, you couldn't always point it straight up because of the point of head angle is still 35 microradians. So you'd still need two separate beams, a transmit beam and a receive beam, and potentially two telescopes. But you could always point them in the same direction. And so I think geostationary is more attractive, although it still doesn't make sense with the latency. That's still 200 milliseconds latency. And yeah, so, but MEO, I think they have, some of these are polar, so potentially that makes sense. Okay, now when it comes to the low Earth orbit backhaul, especially if you have a very dense constellation, you can have very good signal to noise ratios, especially compared to what we were just talking about. And even with the Starlink size terminals, oh, this is with tip tilt. Let's try this with no adaptive optics. So my only concern here would be the expense of the transceivers, because if you were mass producing these and putting them on all the different satellites to do your backhaul, then that would be a concern. But in terms of link budget, you could get a very strong as long as the weather's clear and you're in a good location. And let's just try it in a poor turbulence location really quickly. Okay, so even in a somewhat bad location, especially if you're doing a 350 kilometer altitude, that could be even stronger. I think the bigger concern would be pointing. So you have the turbulence causing fading, but you can also have turbulence causing jitter, and then you could have jitter from just vibrations in your systems on your satellite, and then especially on the ground, especially if these are just some cheap kind of terminals without tip tilt. So that would be number one. Number two would be the weather, and then number three would be the costs of mass producing them. However, if you could do more backhaul than the entire 4 antennas of version 3 with just one optical transceiver, then I could see that being the cheaper option. It's really hard for me to say though. And then since the laser mesh between all the different satellites is so robust, you could just have some locations that have optical available, and then they can spread out that bandwidth or that backhaul capacity to the other satellites through the laser links. And with 2.4 terabits, that wouldn't be unlimited, but that would be substantial. There is the one point of evidence in favor of this kind of backhaul setup, which is that they decided to go with 6 laser links on version 3, when you don't necessarily need 6 laser links, right, to form a mesh. And it would probably be simpler to stick with 3 or 4 and just make them higher data rate per link. And so I think it's possible that they are intending to at least try to use those extra laser links to connect to the ground. And then when they need more capacity in space, they can switch back up into space. That's what I would have said for sure if I had not seen the D-band version 4 system. And with that system, it's just much more reliable. It can go through clouds. It can't really go through a lot of rain, but that's somewhat rare to have heavy rainstorms. And so if I had to choose one, I would probably say the D-band might be better. And SpaceX tends to be really pragmatic about these kind of things. So I think it's just a question of how much are those D-band terminals going to cost, and how mature is that technology compared to this optics technology, which is getting more and more and more mature because of all the optics in data centers, especially, and in just terrestrial communications and fiber. And in fact, it's already pretty mature as it is. They basically just use commercial transceivers in that T-Bird test. And then I'm fairly certain the Starlinks can basically just use off-the-shelf transceivers for their network. So we'll just have to wait and see on that point. That's the end of the technical portion of this video. And now we'll do a conclusion to wrap things up. First of all, when it comes to free space optical communications, I think it has a really bright future, especially completely in space. For links between the Earth and space, I think that will be limited to more of an infrastructure and backhaul role, because the weather and clouds just simply makes it much more unreliable in any given location than RF. For TeraWave specifically, I'm pretty positive about the optical part of the constellation, and I think because it's a small number of satellites, that as long as they can build them to be relatively low mass, then they would be able to launch this realistically, and it seems like they could have a relatively profitable service, potentially. The RF part of the constellation, I'm not as positive about, and I'm not sure that it'll be competitive. So when I first read the FCC filing, I was expecting to see 144 gigabits per link, because that is possible. We know that's possible with the version 3 backhaul antennas. And so it was a little bit perplexing to see that. And then also that the payload was basically exactly the same as Amazon Leo and Starlink, and lower performing. And so I think that part of the constellation definitely needs some work. However, they're going to have time to work on it, because the real challenge in these mega constellations is not any of the satellite hardware, it's the launch.
And so I think pretty much all of these, except for Starlink, are going to continue to be paper tigers because of the monopoly position and the excellence of Falcon 9 and SpaceX compared to the other launch competitors. And you could argue that these other constellations could just launch on SpaceX, but I don't really see that happening because, first of all, SpaceX has their own self-interest. They don't want to launch their competitors. And then they also have an opportunity cost where they're already making more money from Starlink than launch. So launching any other satellite is going to be potentially less profitable than launching their own Starlink, especially in these new versions of Starlink. And then finally, even if these competitors do get allocation on SpaceX, then they have to pay, pretty crazy gross margins, something like 70% or more. And that's just not going to be competitive to what it is costing SpaceX to launch Starlink. And when I look at New Glenn and other competitors, I have to say that they're at least 10 years behind the technology and reliability of Falcon 9. For example, in 2016, exactly 10 years ago, Falcon 9 was having reliability problems. It was exploding on the pad. And now you can see the same thing happening with New Glenn. And that's just because it's an immature technology and they have to go through these iterations to get to the same level of maturity as Falcon 9. The same is true for Starship. And this is a hot take, but I also estimate that Starship is also 10 years behind in terms of cost per kilogram. And this is because people really don't appreciate and don't respect how difficult of a challenge it is for a fully reusable rocket like Starship. And this is truly a holy grail of an engineering program. So for example, Falcon 9 had 0 suborbital tests. They just got to orbit on their first flight. And in the case of Starlink, they've had to go through 13 iterations of suborbital tests. And now they're finally going to do their first orbital test. And even then, they're not going to have nearly anything close to 100 tons of payload. And that's especially true if they're not launching into a low inclination prograde orbit. On the most recent suborbital test, they only launched 20 V3 satellites, so that's something like 30 tons-ish. And so they don't have the best delta V margin because it's designed for full reusability. And even SpaceX and Elon agree, and they talk about how difficult it is. And he says sometimes he wonders if it's even possible. The same is true with the problem of catching the booster. They did this on flights 5 and 7, and then they haven't actually done it since. And now they need to try to catch the ship that will have just re-entered from outer space, which will be even more difficult. So banking in a price of $100 per kilogram for a competitor to SpaceX launching a mega constellation on Starship is just totally unrealistic, in my opinion. So once they do figure out Starship and they have that design fully worked out and fully mature, it's going to take even longer for the competitors to catch up. Because if you think about it, none of them are really being as ambitious and none of them are skating to where the puck is going. They're not designing launch vehicles to be fully reusable. They're just designing launch vehicles to compete with Falcon 9. And even then, no one has been able to successfully duplicate what they've done with Falcon 9 because you can't just copy and paste a rocket design. And most of it is just the technology within the engine, which is all very closely held secrets. So I think a lot of these mega constellations, including the Blue Origin TeraWave, they have some significant challenges ahead unless they are willing to invest more and actually compete with SpaceX on launch. And that's especially true with SpaceX raising something like hundreds of billions of dollars with their recent IPO and fundraising with the banks. And obviously a lot of that is going to AI, but a lot of it will go to the launch side and the Starlink side. And furthermore, if you just look at the satellite technology, because they have all of this business and all of this revenue, they're able to also invest more R&D into the satellites. And that's just another moat. So anyway, I would really like to see some of these other companies step up and truly compete at the highest level of the market. There's also some interesting lore here about Starlink. So when they first started up Starlink in Seattle, they got a bunch of executives from Microsoft and Boeing, and they were moving very slowly on the development. And eventually Elon Musk got fed up and he came in and he fired everybody and replaced them. And then those people, they went and started Amazon Leo or Project Kuiper at the time. So I think it may be time for Jeff Bezos and even Andy Jassy at Amazon to do something like this and really restart these programs and take them more seriously, because the Blue Origin, the motto of going step by step ferociously and all that kind of stuff, I think that's largely failed. And if you look at the first 20 years of their business, they weren't really achieving anything. They were just doing their suborbital launches, launching Jeff Bezos and Katy Perry into space. And now with New Glenn, the moving slowly approach
clearly has also failed, especially since they only built one launch pad and now they're going to have possibly years of delays. Okay, that is the end of my rant, and I'm going to end it there. For my next video, I'm thinking of doing a shorter video. I really want to avoid these deep dives that will go on for hours. They just take a long time to make. However, my next one, I would like to do something with sonar, and then I'm going to make some shorter videos in the meantime. So maybe something about LiDAR or something about space exploration. And you guys can let me know what you want to see in the comments. As always, make sure to like, subscribe, share, and comment what you think in the comments. And with that being said, have a great day.